institute, some colleges, some universities have joined, and some various number of research scholars from various prestigious universities have joined. So I again welcome you all. Thank you so much for your continuous support. So just 2 minutes left. Now around 187 participants have joined for this conference. Dear all participants, please follow the chat box during this presentation for many other information and the attendance link. So I again welcome you, ma'am, Suman, Lata, ma'am, Jain, ma'am. Thank you so much for giving us this opportunity to hear from you. Definitely, I think our participants will learn many things from you and your achievements. So, dear participants, let me introduce Professor Jain. Dr. Suman Lata Jain, ma'am, is currently working as a senior principal scientist at CSIR-Indian Institute of Petroleum, Dehradun. She is heading synthetic chemistry and petroleum's area in chemical science divisions of institute. She obtained her MSc in organic chemistry from University of Rajasthan, Jaipur in 1998 with gold medal. He was a topper of her batch, and she obtained PhD degree in 2004 from HNU Garhwal University, Srinagar. On study, her thesis title was Studies on Transition Metal Catalyzed Organic Transformations. After that, she received Humboldt Fellowship and worked under the Professor Oliver Reiser at University of Regensburg, Germany for 1 year. In 2011, she got a permanent position as a senior scientist in Chemical Science Division at CSIR-Indian Institute of Petroleum, Dehradun. She is a recipient of many awards like INSA Young Scientist Medal, MRSI Award, CRSI Medal, INSA Platinum Jubilee Young Scientist Award, CSI Young Scientist Award, etc., etc. She was selected as a founder member of INYAS in 2015. She is also serving as an associate editor of New Journal of Chemistry (RSC) since 2018. Her research interests include carbon dioxide utilization, photocatalysis, homogeneous catalysis, synthetic organic chemistry, and petrochemicals. Sorry. So with this short introduction, moreover, she has published more than 240 research articles, 7 book chapters, and she has 24 patents. So with this short introduction, we again welcoming you, ma'am. Thank you so much for giving us this opportunity. I think we should not waste further time. Now now over to you, ma'am. You can share your lecture and start your presentation. Thank you, ma'am.
Thank you, Dr. Banerjee, for this kind introduction. So first of all, I would like to express my sincere thanks to organizers and mainly Dr. Banerjee for inviting me and for giving me this opportunity to present my research to you. So today I will talk about the carbon dioxide utilization for the chemicals. So we are mainly working on the carbon dioxide utilization. Why it is needed to work on the carbon dioxide? And so this is the just basic outlines of my presentation, why it is needed to work on the carbon dioxide, why it is a topic of so much concern in the recent years, how we are getting so much CO2 in our atmosphere, what are the routes of the mitigation of carbon dioxide, and how we can use this waste as a feedstock or for valorization, and how we can convert the carbon dioxide to fuels. And mainly our research interest is on the photo reduction of carbon dioxide, or we can say that we are mainly working on the light assisted activation of the carbon dioxide to producing valuable chemicals. So with this introduction, first of all, we know that energy and environment are the two main concerns in the recent years, and both are the interconnected. If we look at the energy scenario of our country, we see that coal is the dominating factor in our energy basket, and it will remain as such, because our more than 50% energy demands are means met by the coal combustion, and coal is the main contributor, or we can say that fossil fuels are the main contributors for the carbon dioxide emissions. So as we are moving towards the development, the world is globally we are moving towards the development, and developed countries, they are emitting more CO2, and developing countries, they are also contributing with this. So what is the source of this carbon dioxide? So we can say that fossil fuel combustion or our industrialization, deforestation, these things are really means contributing towards this carbon dioxide in the atmosphere. So day by day, our concentration in of the carbon dioxide in the atmosphere is increasing, and that is not harming individually as such, we can say, but it is harming our environment. It is increasing the temperature. It is affecting our aquatic life. It is affecting our flora and fauna. So much concern in the recent decades, or mainly the attention is focused on the mitigation of carbon dioxide in the recent years. So if we look at this graph, we can see that fossil fuels are the main contributors of the carbon dioxide. Apart from the fossil fuels, like industries, like for example, cement industries, with this development, we are moving towards the deforestation. So deforestation is also one of the main factors for this carbon dioxide emissions. So what are the effects of this CO2? So CO2 concentration is increasing day by day in our atmosphere, and that is increasing the, as we know that it is increasing the global temperature. That is called the global warming. So what effect of the global warming is means how we are affecting, or how we are getting affected with this global warming. So overall temperature of the earth is increasing. Another factor is that we know that CO2 is an acidic molecule, so it is miscible with the water and produce the carbonic acid. So that that acidification is means making our oceans towards the acid pH. So pH of the ocean water is going towards the acidic side. So this kind of disturbance, like our temperature is increasing, or sudden climate changes, so such kind of things, they are not they are not normal. So with this, carbon dioxide is not affecting only our atmosphere, but is also affecting our aquatic life, because pH of the water is changed, and some of the aquatic life, they exist only at the particular temperature as well as at a particular pH. So if the things are disturbed, nature will disturb, we will also get affected. So this is the main concern, why we are so much worried about this concentration of carbon dioxide. So what we can do now, because we know that if we are moving towards the development, we cannot go back. If we are living in the luxury, we cannot go back in our life in the like in 1940s or 1920s. So what we have to do, so if we look at this picture, if we can mitigate the carbon dioxide, or we can manage this problem, if we, on the demand side, if we switch to the processes which are energy efficient, or we can say that by energy efficiency, or by making the processes energy efficient, we can control some of the carbon dioxide emissions. We can switch to the fuel, because presently we are mainly dependent on the fossil fuels, and in context of the India, we are mainly dependent on the coal. So fossil fuel combustion is one of the main contributor of the CO2 emissions. So if we can switch the fuel, like in the recent years, biofuels, renewable fuels, they are also gaining so much interest. One of the main reasons for switching of the fuel is the problem which is related with the carbon dioxide concentration in the atmosphere. And we can also design some kind of equipments. They can produce our chemicals with more efficiency, or with the more energy, or with the less emissions of the CO2. And another is the carbon capture and sequestration. So this is the practical way, because the carbon dioxide, we can capture it and we can store it. So this is the general term which presently it is being practiced in the recent years. We are capturing the carbon dioxide and we are just storing it in our geological formations, or underground, we are storing the carbon dioxide. On the other hand, if we look at the supply side, we can use the alternative energy sources, like besides the fossil fuels, we can use hydro energy, wind energy, geothermal energy, and solar energy. As well as we can switch from our conventional vehicles to the fuel cell vehicles, hybrid vehicles, solar heatings, electrical vehicles. So these are some of the steps, if we can use or we can start practicing, we can somehow or to some extent we can manage the carbon dioxide, or we can contribute in the CO2 mitigation. So in terms, there are one thing, like we are capturing the carbon dioxide and we are storing it. So in this way, we can say that we are capturing something and we are transporting it, we are purifying it, transporting it, and then storing means we are just dumping. So for this dumping, we have to, this dumping, to reach this dumping step, we have to need a lot of capital cost, because all the steps like capturing of the carbon dioxide from the power plants, from the industries, or from the atmosphere, it needs a lot of capital cost, and after that purification, transformation, or that transportation and storage. So all these things involve the cost, and finally what we are doing, we are just dumping the carbon dioxide. So apart from that, if we switch our thinking towards the use of this waste feedstock, or we can say that if we consider the carbon dioxide as a valuable feedstock, so that we can use it further. So this utilization of carbon dioxide is preferred than the capturing and storing. So we are mainly working on that. So if we look at the scenario of carbon dioxide utilization, at present only some thermal routes are known for the carbon dioxide conversion, like some of the industrial processes like urea production, salicylic acid, ethylene carbonate, methanol. So these are some industrial processes which are known up so far, or which are well established industrial processes from the carbon dioxide, but they are the thermal routes. So they can mitigate, or this is the carbon dioxide amount that can be avoided or that can be used by these methods. So in the short term, what else we can do? We can produce the chemicals as well as the fuels, because so far we are producing on the chemicals by using the thermal routes. And in the short term, if you look at the scenario, we can convert the carbon dioxide into the chemicals as well as in the fuels by using the thermal routes as well as the LD. So in the medium term, we can increase the conversion of the carbon dioxide to the fuel. However, if we see the long term mitigation or long term use of the carbon dioxide, sustainable use of the carbon dioxide, that is none other than the conversion of carbon dioxide to the fuels. It is not only thermal, because other methods we can also use, like electrochemical, photoelectrochemical routes, and as well as the biological routes. So this is the picture that is showing the scenario of the carbon dioxide utilization. Presently, we are converting the CO2 into the chemicals. However, with time, if we have to get a sustainable solution or a practical way, ultimately we have to convert the carbon dioxide into the fuels. As we all know that CO2 molecule is highly stable, because it's a linear molecule and carbon is in +4 oxidation state. So it's a very, very stable molecule. Activation of carbon dioxide requires a lot of amount of energy. So that is the biggest challenge with the CO2 utilization. So apart from the thermal, if we can develop some other methods, like using the electricity, we can activate the carbon dioxide, or by using the solar energy, we can activate the carbon dioxide, or integration of both the things, that is called the photoelectrocatalysis or photoelectrochemical, in which we use the photon energy as well as the electricity for activating of the carbon dioxide. So this is the picture that is showing the scenario of CO2 utilization. So ultimately what we have to develop the processes or develop the technologies for conversion of the carbon dioxide into the fuel, so that the carbon cycle, we can neutral the carbon cycles, because the main source of the carbon dioxide is our transportation. In our transportation sector, emissions are the CO2 is emitting. If we can capture the CO2 and convert it back into the fuel, so that we can make a carbon cycle. But what are the barriers? Why it is not so simple? Because CO2 is we are saying CO2 is a renewable feedstock. It is non-toxic. It is abundantly available, and we are in urgent need to convert it or to utilize it or to mitigate it. So what are the barriers? Why we are not getting so much success? So the main barrier is the cost of CO2 capture, because capturing of CO2 is not so easy, because in the atmosphere we see it's a ppm, it is in the ppm level. So how we can capture the carbon dioxide from the atmosphere? It involves a lot of cost. Carbon dioxide can be captured from the source like power plants, because from the power plants the maximum CO2 emissions occurred in our power plants. So we can capture, but everything involves the cost. So one of the major challenges behind the CO2 utilization is its cost, high cost in capturing, separation, and its purification, and then transportation. Ultimately, we have to capture the carbon dioxide, we have to purify it, and we have to transport either for the utilization or for the storage. So every step is involved a lot of capital cost. So this cost is one of the main barriers. And another barrier is its chemical inertness, because as I said, the carbon dioxide molecule is highly stable. Its thermodynamic and kinetic stability is so much high. So it requires a lot of energy for activation of the carbon dioxide. So energy requirements for the CO2 chemical conversions are very high. And another thing is that the lack of industrial commitments for enhancing CO2 based chemicals. We know our most of industries or our most of industrial products, we are producing from the syngas or carbon monoxide. So switching from the carbon monoxide, to carbon dioxide itself a biggest challenge, because our all industrial processes are well established, industries are well established, so they don't want to switch, because for switching they have to change the infrastructure, they have to take the risk, and they have to see other parameters, cost, feasibility, and many more things. So and lack of socio-economical driving forces. So the switching from the carbon monoxide or switching from the existing processes towards the carbon dioxide, it needs, what is the driving force? Only driving force is that CO2 is abundantly available, but its availability for the utilization is very, very low, because it involves a lot of cost, it requires a lot of energy for activation. So these are some factors which are the barriers in the CO2 utilization. So this is, if we look at the practical applications of the carbon dioxide, we can produce the value-added chemicals. As I said earlier, CO2 is a very a renewable feedstock. It's a C1 feedstock. So if we practical or theoretically, we can convert carbon dioxide into any chemical, because any organic compound that should have carbon, and without carbon, organic compounds cannot exist. So we can convert the carbon dioxide into any organic chemical or organic compound. We can also produce fertilizer. So this is the largest use of the carbon dioxide. Okay, we are producing the urea from the carbon dioxide. And this is a non-chemical use. We can use the carbon dioxide into the enhanced oil recovery. So what is the enhanced oil recovery? As we know that we get the oil from our by digging from the earth. So for increasing the oil production, we pump the carbon dioxide at very high pressure. So it means it increase the availability, or it increase the recovery of the oil from underground recovery. It increases the recovery of the oil. So for that we can also use the carbon dioxide, but it is a non-chemical use, because here we are just pumping the carbon dioxide and recycling it, and after the certain time we have to leave it in the atmosphere. But if we are converting the carbon dioxide into the chemicals, means we are fixing the carbon dioxide and we are converting the carbon dioxide into the other chemical. And this is the sustainable way, or this is the sustainable approach by which we can really contribute, or significantly we can contribute in the problem by converting the carbon dioxide into the fuels. So if we look at all these possibilities, by using, we can produce the chemicals, fertilizers and non-chemical uses, as well as conversion of carbon dioxide into the fuels, we can mitigate 10% of the total emissions of the carbon dioxide. Among this total 10%, if we look at the chemicals, if we start converting every chemical, or if we start producing every chemical from the CO2, so we can only mitigate about 1%. So this amount is very less. So for the practical solution, or for the long-term application, ultimately what we have to find out, the way we have to use the CO2 for the conversion of fuels. so that we can significantly contribute by the chemical fixation method. We can mitigate the CO2, or we can, in real sense, we can valorize this waste feedstock. So this is the how we can convert the carbon dioxide in the fuel. So it's a long-term solution, but it has itself has some drawbacks. The one of the main drawbacks is that it is highly stable. Stability of the carbon dioxide molecule, it's the biggest issue. So but this is a long-term utilization of the carbon dioxide. Conversion of fuel can provide the two benefits. One is the fuel recycling, because we are using the fuel, we are getting the carbon dioxide in the emissions, we are using that CO2 again for the conversion to the fuels. So by this way we can recycle the fuel, and ultimately what we can do, we are controlling the emissions. So it's a beneficial approach, but the problem is that it is very highly stable molecule, so it requires a lot of energy for the transformation of the carbon dioxide into the fuel. So in thermal processes, if we imagine we are converting the carbon dioxide, if we are imagining a reaction of CO2 with the hydrogen in thermal catalysis, at least we have to give 500 or 600 degree temperature for reaction to occur. So if we can imagine at this temperature, only heterogeneous catalyst will work at this temperature, and the CO2 and what are the other solvents and everything, they will emit the more carbon dioxide, because every organic molecule, if it is combusting or if we are heating the organic compounds, ultimately they produce the carbon dioxide. So in thermal catalysis, there are some drawbacks. One drawback is that if we have to provide a lot of temperature, so that temperature ultimately lead the deactivation of the catalyst. How that deactivation occurs? Because the other organic compounds, organic molecules which are present in our reaction system, they burn and produce coke or carbon, or we can say that other gases like carbon dioxide or carbon, and then that carbon deposited on the active sites of the catalyst, that lead to the deactivation. So in thermal catalysis, they have certain limitations. Probably we are using carbon dioxide as a feedstock, but in real we are emitting the more carbon dioxide. And catalyst deactivation is one of the main drawbacks. It's an obvious drawback of the high temperature reactions. So besides this approach, what we can do? So we are using the photons as we can use the photons as energy sources, like that is called the photochemistry, or we can use the electricity as an energy source. That processes are called the electrochemical. So thermal reactions are our research area is mainly focused towards the light assisted CO2 activation. So I would like to emphasize the difference between both the things. If we imagine the thermal processes, and on the other hand we are thinking about the photochemical, so we can see the difference in thermal catalytic reactions. They occur from the ionic routes like cations and anions. They are produced and they are finally converted into the products. On the other hand, our photochemical reactions, they lead by the radical route and single electron transfer reactions. Photochemical reactions are single electron transfer reactions. They produce the radicals, and after the radicals, they couple and they provide the desired chemical. Our thermal reactions, they require higher temperature for the CO2 activation. However, in solar or in photochemical reactions, only solar energy, which consists the 45% of the visible light, it produces the photons, and that photons, they activate the carbon dioxide. In thermal catalysis, we need to give the temperature like 400 degree, 500 degree, 600 degree, and so forth. However, in the photochemical reactions, they occur at the ambient conditions and ambient pressure. So the deactivation of catalyst is more prone in the thermal catalytic reactions. However, there are minimum chances or negligible chances of the deactivation of the catalyst in the photochemical, because photocatalysis occurs as the ambient conditions and ambient pressure conditions. Mainly at room temperature, we can proceed with the photocatalysis. So with this advantage, how the thermal catalysis works and how the photochemical reactions work and what are the benefits of our photocatalysis. So we have chosen this. We have chosen this area of research for finding the solution for CO2 mitigation. So this what is photo reduction is nothing but is inspired by the nature, because we know that in the nature photosynthesis occurs. If we are carrying that photosynthesis in our lab, that is called the artificial photosynthesis. In nature, the catalyst, photocatalyst, the chlorophyll. In the labs, we are producing or we are designing our catalysts. Those are the artificial photocatalysts. So we are just mimicking the nature in our laboratories. So our main emphasis is to activate the carbon dioxide under the ambient conditions to get the valuable chemicals without the deactivation of the catalyst and with the minimum cost, or with the using the cost-effective catalyst. So if we look at a general photocatalytic reaction, it is a semiconductor. When we irradiate the photocatalyst, charge separation occurs and electrons move from the valence band to the conduction band. So it creates the hole. So those holes, they are used for the oxidation reactions, and the electrons which produce in the conduction band or which transfer from the valence band to conduction bands. So electrons are available in the conduction band for the reduction reactions. So in case of the CO2 reduction or conversion of CO2, the first step is always the reduction of carbon dioxide to its radical anion, and it occurs at the conduction band. However, the oxidation of water that provide the necessary electrons for this reaction, as well as the protons for the conversion of or for the reduction of carbon dioxide. So it's a general mechanism how this system works. So similar to the catalysis, our photocatalysts are also two types: homogeneous photocatalysts as well as the heterogeneous photocatalysts. Heterogeneous photocatalysts, they are semiconductors, metal oxides, mixed metal oxides. One of the main well-known photocatalysts is the titanium. And homogeneous photocatalysts, they are none other than the molecular complexes, transition metal complexes, which are homogeneous in nature because they dissolve in the reaction medium, they bind with the CO2. So similar to the catalysis, photocatalysts can be designed in the two ways: homogeneous photocatalysts and the heterogeneous ones. Heterogeneous photocatalysts are semiconductors. They react with the but they have certain drawbacks. Heterogeneous in the literature, if we put the keyword photo reduction of carbon dioxide, lot of semiconducting materials, they just in a one click you can find a lot of, means beyond our imagination, lot of materials are there to activate the carbon dioxide, but they have certain drawbacks. Like as I said earlier, in the photocatalysis, the first step is the charge separation, electron hole pairs. That step is the crucial step in the CO2 reduction, because if the hole exists in the conduction band, then only they can use for the reduction. If the electron hole pair is recombines or electron come back into the valence band, means the reaction will not take place. So these are the some drawbacks with the semiconductors. They absorb the light, they provide the charge separation, but recombinations of these charges or charge carriers occurs, or that recombination of the electron hole pairs occurs, and so that available electrons for the CO2 reductions, they suppressed. So these are the drawbacks of the semiconductors. On the other hand, if we look at the molecular complexes, so they have certain advantages. One of the main advantages of the molecular complexes is that they can combine with the CO2 as a ligand. So they can combine the CO2. By this, they can increase the concentration of the CO2 in the reaction medium or at the active sites. And also, molecular complexes, they take part in the reaction by transferring the single electron, that we will discuss in further slides. But the drawback of molecular complexes, like we know that molecular complexes, they are associated with the obvious advantages of the homogeneous catalyst, like they are very difficult to recover, and they are non-recyclable after the reaction. So it is very difficult with the homogeneous system. It is very difficult to get the product or purification of the product after the reaction, because catalyst is also dissolved in the same reaction mixture. So if we look at the semiconductors, this is the simple semiconductor. Electrons light, after the light absorption, charge transfer occurs and electrons are present in the conduction band. They provide the reduction of carbon dioxide. However, oxidation of the water takes place at the valence band. that provide the electrons as well as protons for the reduction process. So due to the two are the main things. The one is the band gap. So the on those semiconductors which have the band gap equal to the photon energy that photons can be absorbed. So for the visible light absorption, the band gap should be minimum. Like titanium, if we see, the titanium is a very, very well-known semiconducting material, but it works under the visible light because it has a higher or wider band gap, like 3.2 electron volt. So for the in the light spectrum, if we look at the solar spectrum, it contains only 5% UV as well and 45% of visible. So what kind of materials we need to design for the photocatalysis? We need to design the materials that should absorb the visible light, so that we can see the real applications of the solar energy without without designing of the, because for the UV light applications of the UV light, we need to have the special equipments. However, for the visible light, like the light we are using in our daily light, so that is means matches with the visible light. So the material should be absorbed in the visible light, and for that this band gap should be minimum. So what we can do, or how that we can tailor that band gap. So some band gap engineering processes are known. So this is, if we support our metal oxides like titanium oxide, if we support our titanium oxide to any other support, then this mechanism will work. The support will play a role, and it will change the band gap, and that will absorb the energy. Electron hole pairs occurs, reduction occurs, and here oxidation occurs. One of the main another approach is that we can use the co-catalyst as well, or we can say the heterojunctions. This is our main semiconductor and this is our co-catalyst. So electrons, when the charge separation occurs, electrons are moving in the conduction band, and these electrons, rather than jumping back to the valence band, these electrons come in the shells of the Fermi levels of the another co-catalyst that we are using, or doping metal that we are using for engineering of enhancing the CO2 reduction. So these electrons will come in this Fermi level of the co-catalyst, and make those electrons can participate in the CO2 reduction. And another process for modification of the semiconductors is the dye sensitization that we are working. Like it's a homogeneous metal complex. Metal complexes can be deposited, can be grafted on the semiconducting supports, and they have various advantages which I will discuss in next slides. So this is the metal complex. Complex can also absorb the visible light and provide the electrons. So these electrons, so the conduction band of the semiconductor is not only getting the electrons from the valence band, but also it is getting electrons from the metal complex. So compared to a normal semiconductor, if we look at the dye sensitized semiconductor, we can see the electron availability is higher, and reduction totally depends on the availability of the electrons. So as much as electrons will be available, the reduction process will be higher. So these are some ways by which we can enhance the conversion of carbon dioxide. So this is basically a literature reports. If we look at all these things, most of the materials are semiconducting materials, and they are giving yields of the reduced products. By the CO2 reduction products, lot of products can be produced from the CO2. It can produce carbon monoxide, formic acid, methanol, and ultimately it can give the methane. So different materials produce different compounds or different chemicals from the CO2, but yields remain very low. So far we can see the main obstacles in the photo reduction of carbon dioxide. The one is the conversions are very low, because only we get product yield in the micromoles, millimoles. So these are very low conversions. And selectivity of the products is also in generally we get the mixture of products, like in a mixture we are getting carbon monoxide in the gaseous phase and formaldehyde, formic acid, methanol in the liquid phase. So these are some drawbacks. So such kind of drawbacks can be managed, or what is the need of the research? We have to design the materials in such a way those can give the higher convergence as well as the selectivity of the products. So apart from the semiconductors, due to the some advantages of the molecular complexes, we focused our area of research towards the use of homogeneous metal complexes. So if we look at this, these are the homogeneous metal complexes. So if we look at those structures of these complexes, they are they are having a lot of unsaturation or conjugation. So due to this conjugation, they always absorb the visible light. So if we that unlike to the semiconductors, metal complexes, they are more visible light absorber. And this is our metal cation. And if we look at the structure of carbon dioxide, it has 1 carbon and 2 oxygen. So it's a nucleophilic oxygen also. So it can bind with our central metal atom. So when it binds with the central metal atom, means it is increasing the concentration of CO2, or it is making the availability of the CO2 with the active sites, and that will ultimately increase the conversion of the CO2. So these are some advantages of the molecular complexes. It can bind with the CO2 to provide the higher concentration of the carbon dioxide. They are well absorb of the visible light, so there is no problem with the tailoring or with designing. And one of the main thing, the complex, which we can design a complex by playing with the central metal as well as the ligand. So by playing with those things, we can design our complexes in such a way to get a selective product from the CO2. But so this is the basic mechanism of this reaction. As I said earlier, the metal complexes, they itself take part in the reaction. So first step, they absorb the visible light, they undergo in the excitation state, and in the excitation state, because when they take part in the reaction, means reduction occurs at the metal complex, they need to have the electron availability. So they take the electrons from some sacrificial electron donors, which we have to use in the CO2 reduction if we are using the homogeneous complexes. So these sacrificial electron donors, they are nitrogen compounds like ethanol amine, triethylamine, those kind of compounds. So they provide the electrons, and these electrons are used for the CO2 reduction, and ultimately that sacrificial electron donors, they convert into the various products. So if we look at all these steps or all these things, it has 2 drawbacks with the molecular complexes. One is their homogeneous nature. We cannot recover those complexes after the reaction from the reaction mixture. And another drawback is that we have to use the sacrificial electron donors. Those are decomposing up in the photocatalytic medium, or under the photo conditions, they are decomposing in the several other compounds. So for conversion of CO2, we have to sacrifice another molecule also. So these are some drawbacks. And other thing is that that molecular complex structure, they have metal cation and ligands. So all these ligands are organic compounds, organic molecules. So there are always possibility for the photo degradation of these complexes in the presence of light or under the photocatalytic conditions. So means they are less robust. There is always possibility if we are getting methanol. So it's always a confusion that methanol is coming from the CO2 or it is coming from some ligand. So these are the certain fundamental problems with the molecular complexes. So to tackle with this problem, what we have done, we are using the molecular complexes as the photosensitizers and immobilizing those photosensitizers to some supports. So we are using such kind of hybrid systems. It is our semiconducting support. It is our metal complex. So this metal complex is acting as a photosensitizer, means this is absorbing the light, and electrons are going from HOMO to the LUMO, and these electrons are moving in the conduction band. So if we look at this mechanism, because that semiconductor is also can provide the charge separation under the light irradiation. So it is providing the electrons, and also the metal complex can also provide the electrons. So if we look at this, the metal complex is acting like an antenna. So it always pumping the electrons in the conduction band. So electrons are readily available in here for the CO2 reduction. And when we are immobilizing the complex, means we are increasing the stability, because in the heterogenized form, it is heterogeneous in medium. It acts as a homogeneous, but in the reaction medium, its phase will be heterogeneous. So it will not dissolve in the reaction medium. We are increasing the stability. So due to these advantages, we have selected the hybridization or immobilization or transformation of the homogeneous complexes to the heterogeneous forms. So this is our basic research work, what we are using and why we are using. So now I will discuss about our recent research. So this is our first paper that we published first time in 2014 using our hybrid approach. Here we use the graphene oxide. Graphene oxide is a carbon support which is having the oxygen functionalities and prepared from the graphite. So for graphene oxide we have used the support. To increase the functional group, we further functionalize the graphene oxide, and this is our cobalt phthalocyanine. So we are using the cobalt. Cobalt is a low cost metal, and phthalocyanins, they are very easily prepared. Within 5 minutes, you can prepare the cobalt phthalocyanine or phthalocyanine complexes of the metal. Within 5 or 10 minutes, you can prepare in the labs. So we use the functionalized cobalt phthalocyanine as our molecular complex, and graphene oxide is a photoactive support because it is reported in the literature that graphene oxide itself acts as a semiconductor. So, but here we use for the hybridization or for making the hybrid systems. So if we look at the performance, we use that hybrid system. This is our final hybrid catalyst or hybrid photocatalyst that we used for the CO2 photo reduction. If we see the performance, so our the C is our hybrid system. C is our hybrid system that provided the yield of the methanol much larger than the individual components. So that further proved that hybrid systems are superior than their individual components. Why these hybrid systems are superior? So we can see in the mechanism, because both the components have the synergistic effect, like the metal complex that is absorbing the light and providing the electrons in the conduction band. If we imagine the individual components, in individual component, the reaction should take place at the cobalt center. And so, but in the hybrid system, that cobalt electron, the electrons from the complex unit are moving in the conduction band, and the electron reduction is taking place at the conduction band. So due to the synergistic effect of both the components, the efficiency of our hybrid system is much larger than the individual components. So to see the effect of both the components, why it is needed to have the covalent immobilization or chemical attachment of both the components, we also use a physical mixture. But physical mixture, although it provided the higher yield of the methanol, but is much lesser than the hybrid system. So well connected components or when collected homogeneous complexes with semiconducting supports through the chemical attachment, they are robust, they are highly efficient, and they provided the much larger conversion in comparison to their individual components. Similarly, in this work, we prepared the ruthenium based complexes. Like here, I would like to say we use triethylamine as a sacrificial electron donor. So this system has we could solve one problem. That one problem we could transform the homogeneous complex to the heterogeneous one, so that we could easily separate after the reaction, and that system showed recyclability up to 4 or 5 cycles. But here we had to use the triethylamine as a sacrificial electron donor. So to replace or to remove this, we have to find out the ways. So in the next work, we designed the ruthenium multinuclear complexes. This kind of complexes, this ruthenium complexes, the heteroleptic, they have 2 kinds of ligands. So it's a heteroleptic ruthenium complex. Again, we functionalized the graphene oxide support, and we chemically immobilized our ruthenium complex to this support and used for the reduction of carbon dioxide. So if we look at this graph, these are all the individual components, and it is our final hybrid catalyst. So final hybrid system showed much improved efficiency for the CO2 reduction and much higher yield of the methanol in comparison to the other possibilities or other components. So mechanism is the simple. So here the one of the main thing or one of the exciting feature is that we did not use the sacrificial electron donor. So graphene oxide support itself provided the electrons to the complex. Those electrons are used for the CO2 reduction. So by this way we could remove the use of sacrificial electron donor. So it is advantageous than our previous work. So with such kind of designing of some hybrid, means with the playing with the metal ligands and supports, we designed a lot of systems, and we have published more than 50 articles in the recent 5 or 6 years on this subject using the photo reduction of carbon dioxide to the selectively methanol. And one is main thing is that we got only methanol as a reduction product in our all the systems without having any evidence for the formation of gaseous products as well as other liquid products. So these are some important features of my research. Other than the methanol or other than the photo reduction, we are working on the conversion of carbon dioxide to some valuable chemicals. Like here also we designed or we developed some molybdenum based composites or cluster molecules. Those clusters we immobilized on the graphene oxide and used for the reaction of carbon dioxide with the methanol to produce the dimethyl carbonate. So this was although first report where we use some kind of this kind of hybrid system for producing the dimethyl carbonate. So another exciting work is the conversion of epoxides to the carbonates. As we know that cyclic carbonates are very important molecules. They have a wide range of applications like ethylene carbonate. It is used as a solvent in the lithium ion batteries, and carbonates are being used as solvents and polar aprotic solvents and for some reactions and cosmetics as well. So far a lot of literature is known for the production of cyclic carbonates from the epoxides and carbon dioxide. But those thermal methods, they have certain drawbacks, like they are using either they are using the high temperatures, or they are using the homogeneous complexes, or they are using some co-catalysts or additives for the reaction. So before our work, there was no report on the literature, there was no report known on the conversion of carbon dioxide epoxides to cyclic carbonates using the photocatalysis way. So in our work, we supported the cobalt halocynin on the titania and developed a hybrid system. So this was the first report where cobalt halocynin was used as a complex to support on the titania. This hybrid system, it provided the cyclic carbonates in excellent yields, more than 90% conversion at the room temperature as well as the atmospheric pressure. However, in the literature, if we see either temperature is higher or reaction time is higher, or we can see yields are, or the homogeneous systems are known, means homogeneous catalysts are known, or in some cases higher pressure of the CO2 is required. But here we use the atmospheric pressure of the carbon dioxide and perform the reaction at the room temperature to get these cyclic carbonates. So here the mechanism is same like our metal complex that absorb the visible light, and it provide the electrons from HOMO to LUMO in the excited state. The electrons from the LUMO transferred to the conduction band, so that the electrons are easily available for conversion of carbon dioxide to radical anion. However, our organic compound like this epoxide, it oxidized at the valence band, and in the next step, coupling of this anion radical and cation radical to produce that cyclic carbonates. So similarly, another work we performed is the N-formylation reaction. As we know that carbon nitrogen bond formation is a very important reaction, and mainly in conventional methods they use the carbon monoxide or formic acid for the formylation reactions, and they have multiple applications. But we know that use of carbon dioxide in place of the carbon dioxide is desired because CO2 is a non-toxic and abundantly available and safe feedstock rather than the carbon monoxide that is toxic. So in our work, we use carbon dioxide in conjunction with the amines using some kind of semiconducting material. It's a heterojunction material. Here we did not use the metal complex, but it is a heterojunction kind of semiconducting material. And apart from the molecular hydrogen, we use phenylsilane as a hydrogen source, and the reaction occurred at the room temperature to give these formamides. So again, the CO2 activation using the light, we are performing the reactions at the ambient conditions of the temperature and pressure. So a lot of compounds, lot of amines we tested for the reaction to get these formamides. So recently we started this work, the carboxylation reactions. So we know that carboxylic acids, they are a very important feedstock for further reactions. They are extensively used in the polymer industry, in the plastic detergents, and so on and so forth. And market is increasing. Carboxylic acid market is increasing day by day. The conventional approach is use the hydrogenation of the carbon monoxide, but disadvantage, it's an obvious disadvantage, like CO is undesirable due to its toxicity. So use of carbon dioxide in place of the carbon monoxide is always advantageous. There are some catalytic methods are known in the literature, but before our work, but these catalytic methods or thermal catalytic methods, they have their own disadvantages. One is the higher temperature and stoichiometric amount of the organometallic complexes they used. So, but there were only few reports are known on the photocatalytic carboxylation reactions. So before our work, only one report was there for the carboxylation of styrenes that uses the rhodium homogeneous complex. However, so this rhodium, we know that rhodium is a rare metal. So it, and also this is a homogeneous catalyst. So it again, it is not a cost effective metal. It is homogeneous. So it has a, and another drawback is that with the carboxylation, the literature known method provided the hydrogenation. So this is the benchmark process that we improved or that we developed or we used for our reference. And in comparison to this, we developed a nickel based catalyst. Nickel is a quite low cost metal in comparison to the rhodium. And in our systems, we obtained the carboxylic acids without any evidence for the hydrogenation, and higher conversion selectivities are higher, and we did not use any co-catalyst. And also our ruthenium complex we supported on the nickel oxide. So this system was hybrid system, and this is the heterogeneous one. We could recycle, we could easily recover the catalyst from the reaction mixture after the reaction, and we could easily recycle it. So this is our work. Again, the mechanism is same. The metal complex provide the electron on the conduction band. That electron convert the CO2 to anion radical. However, the oxidation of carbenes takes place at the valence band to provide the cation radical. The coupling of these things provide the carboxylic acids. So we use the nickel based support. This is the heterogeneous systems, and the reactions occurred at the atmospheric pressure as well as the room temperature using the 20 watt LED bulb. In most of the reactions, we are using the 20 watt LED white light as a radiation source. And another advantage of this catalyst was it's a magnetically separable. So after the reaction, we placed a magnet to the vessel and the catalyst separated very easily. We decanted the reaction mixture and washed the catalyst and can be reused in the further run. So recently, we developed a very breakthrough process for the production of acetic acid from the methanol using the cobalt thiocyanine attached with the octasulfur. So it's a very unique reaction. In the literature, there is no report known on the utilization of carbon dioxide for the acetic acid in the photochemical conditions. These are the commercial routes which are known for the acetic acid production, but all these routes, they use the carbon monoxide. So the development of a process or the use of the carbon dioxide as a alternate of the CO is very desirable goal. So in the literature, if we see, only two processes are known, but they are thermal. They are using the homogeneous complexes at the higher temperatures. In contrast to this, our process is at room temperature, atmospheric pressure, and we are using the heterogeneous system. So this is the first report or first breakthrough process for development of acetic acid from the methanol and CO2. So that process we have patented it. So these are the related optimization of the reaction parameters, like among various solvents, only dimethyl acetamide or dimethyl formamide, those give the higher performance because these solvents are the CO2 philic solvent. They can capture the carbon dioxide, and when they are capturing the carbon dioxide means they are increasing the availability of the CO2 in our reaction medium. So they are giving, obviously they are giving the higher convergence. So similarly, catalyst doses only 1 mole percent catalyst was found to be optimum. With the increasing of the concentration of catalyst or COPC, while we increasing the concentration of the catalyst in our reaction medium, the reaction decreased due to the overcrowding of the catalyst in the reaction medium. So the availability of the active sites for the CO2 molecules reduced. So these are our developed system was heterogeneous. We could easily recover the catalyst after the reaction and recycled it successfully for various runs. So this is the simple mechanism. That mechanism we established based on the DFT studies, theoretical calculation, controlled experiments, and characterization of the intermediates. So basically, with all these control experiments and other things, we could conclude that carbene is the reactive intermediate in the reaction. So first step is the carbene formation that goes that further react with our molecular complex and finally give the acetic acid. So recently we also developed a work on conversion of, this is also oxidation reaction. So far, if we look at the literature, carbon dioxide reduction is very well known. But using the carbon dioxide as an oxidant means carbon dioxide can provide the oxygen and convert simultaneously into the carbon monoxide is very, very limited reports are known. So in this system also what the carbon dioxide acted as a oxidant. It provide the, it's a dehydrogenation reaction and carbon dioxide is acting as a soft oxidant. So it's but in our system it is the oxidation of benzylamine to benzylamine is occurred with simultaneous reduction of carbon dioxide into the methanol. So such kind of studies we are currently working in our in our lab. So here the catalyst that was used is the copper 1 supported in the graphitic carbon nitride. So these are the optical properties of the catalyst. This is the PL, photoluminescence spectra. This gives the information about the recombinations. So we can see that intensity of this band is so high in the individual components. However, in the hybrid system, it is so suppressed. Means our hybrid system is suppressing the electron hole pair recombination to much larger extent, and therefore it is providing the higher yield or higher convergence. So these are the further characterization ki by these techniques we could confirm ki the design material was successfully prepared. And these are the reactivity. We are giving with the oxidation, along with the oxidation, the carbon dioxide reduction is also occurred. And among the these are the components. This is carbon nitride. This is copper oxide, cupric oxide, that copper 1 oxide, and this is the hybrid system. Hybrid system is much more efficient in providing the higher yields and convergence. And similarly, we prepared the different materials with different compositions. So among all these things, only 1.5% loading of copper 1 oxide to the graphitic carbon nitride was found to be optimum for the reactions. These are the recyclability experiments. The developed material was quite stable, recoverable, and recyclable. So with these findings, we can conclude the carbon dioxide, utilization of carbon dioxide is a very, very recent area of research interest, and it has a lot of scope. Recycling of carbon dioxide either into the fuels or in the chemicals is the only sustainable way for the CO2 mitigation with the value addition. So in view of the current scenario, if we say that due to the higher stability of the carbon dioxide, thermal processes, they have drawbacks of having the co-deposition or deactivation of the catalyst. So we have to look to the alternative ways. Like we have to find the ways to carry out the reaction either using the renewable energy sources like the solar energy, like the photocatalysis, electrocatalysis. So these are the future. And apart from the semiconductors, metal complexes, they can be explored for the carbon dioxide utilization because they have the tendency to bind the CO2 and to participate in the reactions. So they can also explode for the reaction. So if we can do renewable energy, like we can electrolysis from the water, we can produce the hydrogen, and from the atmosphere we can use the carbon dioxide, and by combining the both we can get the fuel. So this is the really a net zero carbon dioxide cycle. This is the real sustainable solution that is our ultimate goal, and a lot of people are working in this area. Although a lot of research is being carried out all over the globe on the CO2 utilization, but all the things are at the at the lab scale level. There are very few technologies. So in the technology is the future. So ultimately we hope with such developments very soon we will have some viable solution for the mitigation of carbon dioxide. So at last slide I would like to say, like to To promote this journal, I am an associate editor of this journal, and it's a very multidisciplinary journal. So I request to all of you to consider this journal when submitting your paper. It's a journal of Royal Society of Chemistry. It's a very reputed journal and provide very good articles on multidisciplinary, starting from the catalysis to the biocatalysis. So last but not the least, I would like to acknowledge the organizers of the conference to provide me this opportunity, director of our institute for always his kind support, funding agencies like CSIR, DST, DBT and CEFIPRA for financial assistance of all this research, and my research team, my PhD students and other research collaborators, both nationally and internationally, who always supported me well in providing the technical support as well as the synthesis, characterization, and whatever I wanted. I always am blessed with having the lot of good people in my life. So with this, once again, I would like to thank you for all your kind attention. Thank you so very much.
Thank you so much, ma'am. Thank you so much for your valuable lecture. I think our participants have learned many things from you, like carbon dioxide utilization, and you have nicely explained how you can utilize this carbon dioxide for various to synthesize various scaffold, like for N-formylation and carboxylation reaction, and you have nicely explained the mechanism also, how this heterogeneous catalyst utilize playing the role to capture the carbon dioxide. Thank you so much, ma'am. And our next speaker, Professor Ranu, is also available with us. So before that, one or two participants, if you have any questions or if you want to share your views, please unmute yourself and you can share directly with ma'am. Yes, Ashish Mathur.
Thank you, ma'am, for nice presentation. And some question like how would you prepare like acid, copper?
How? Please repeat your question. How we prepare copper?
No, ma'am. Acid containing acid and cobalt photo PC something.
Actually, I am not getting the question properly. Maybe there is some disturbance in the voice, or I am not getting. There is some problem.
Ashish, one thing you can say, one thing you can do, please write or email to me. I'll share the same email to ma'am, and then
yeah, definitely anytime.
Is there any participants? Next, this. Any other participants? There are many messages for you, ma'am. They are saying it's a very nice informative lecture and thank you so much and all this thing. So thank you so much, ma'am. Thank you so much for your valuable time, ma'am. We are very much grateful that you have agreed to deliver your so nice work, and all the works you have published in a so reputed journals, SCS Sustainable Chemistry, Green Chemistry, all are highly impacted journals. So thank you so much, ma'am, for your valuable time. Thank you so much.
Thank you. Thank you.
Good afternoon, madam.
Yes.
Good afternoon, madam. I would like to know the cost that is involved in the production of such chemicals from carbon dioxide. This is Dr. Sirisha from Warangal.
Yeah, actually, ma'am, cost and because all the reactions we have done so far in the lab scale level, it's a very small level, like 60 ml vessel. We are performing the reaction in the batch scale. So as such, we don't know the cost analysis because, for some processes like acetic acid production and for carboxylation, we are collaborating with our sister lab CSIR-IICT. So they are developing the continuous process, and after some time, I think I can comment on the cost. But with the literature known methods, or by the comparison of the literature, we can say that we are using the cost-effective material and we are reducing the energy in our system. So exact cost, I cannot comment at this moment. Sorry.
Okay, madam. That's fine. No problem, madam. Thank you. Thank you. Very interesting. Thank you, ma'am. Thank you, sir, for the opportunity.
Thank you so much. Thank you so much, ma'am. So, ma'am, request to Professor Brindaban Chandra Ranu, sir, please unmute your mic. Sir, can you hear me?
Yes, I can.
Yes, thank you so much, sir. So, dear participants, let me introduce our next speaker, Professor Brindaban Chandra Ranu, sir. He will deliver his lecture on functionalization of unactivated CH carbon hydrogen unit, a green concept. Let me introduce sir. Professor Ranu received his MSc from Calcutta University and obtained PhD from Jadavpur University in 1982 under the supervision of Professor Ghatak sir at Indian Association of Cultivation of Science. He did his postdoctoral work for Virginia Tech USA University, and then he became the professor in 1996, senior professor in 2006, and served as head of the of organic chemistry department during 2003 to 2008. He retired from the regular job in 2013, but he still continue his research work, and currently he is in serving as a INSA honorary scientist. He is a fellow of Indian Academy of Science and in Indian National Science Academy. He was offered J.C. Bose National Fellowship by DST and Government of India. He served, and then he is a member of editorial board of so many journals, and he supervised 36 PhD students, guided 36 PhD students. He published more than 290 publications. His H index is so high, 66, and I-10 index is 222. So with this short introduction, I don't want to waste any further time, because now I am requesting Professor Ranu, please share your slide, and we have made you already, we have made you host, so you can share your slide now, and you please start your presentation. Over to you, sir.
Just a minute. Can you see my slides?
Yes, sir.
Fine,
Please
fine.
click. Yes, yes. Now it is visible, sir. Please make it full screen.
So, okay. Yes. Is visible?
Yes, sir.
Okay.
Please make it full screen. Yeah,
Yes, full
now
screen.
it is okay, sir.
Now it's full screen.
Yes, sir. Yes. Thank you so much.
Okay. Thank you, Bubun, and the organizer for inviting me to this virtual international symposium. And that's the new normal. Everywhere is going on. That is convenient also in one way. Someone from Spain, someone from US, or any country can join without taking the trouble of traveling. Yes. Okay. And what I'm going to talk today, as the title says, the functionalization of unactivated CH unit, a green concept. Let me start with what is unactivated, what is activated, and why it's green concept. So activation, what is activation? Why we call it activation? If you look at this simple benzene molecule, and if you want to functionalize any of the carbon atoms here, it's not that easy because it's unactivated. But how can we make it easy and how the reaction goes? If you put a functional group here, then the life is simple. Like if you have an iodide here, then you can have a nucleophilic substitution by other molecule and you can functionalize at this position. So at the cost of this functional group, you cannot the living group, or this is the living group, you can have functionalization here. So that is the definition of unactivated, and this is now somewhat activated. Activated by the presence of a functional group. But if we want to make simple functionalization of unactivated unit like this, what we have to do? In that case, we can have a directing group. That can be some heteroatom containing material, and this directing group, and if you add some metal, particularly palladium, then you can make a like metallocycle like this, and then this position is now activated. Now, if you put some nucleophile or any other reactive substance, that can now react here. So if you look at back from this to this is unactivated, And this is now, you can functionalize here in presence of a metal, in presence of a directing group. Let us come to some real example. Here, the Suzuki coupling, all of you know how that Suzuki coupling occurs. It's a reaction of an aryl boronic acid and an aryl halide. In presence of palladium, you can make a bi-aryl. Actually, it's a formation of a carbon-carbon bond. This carbon bonds with this, binds with this carbon. But while doing so, you are losing a functional group boronic acid and also this bromide atom. So this reaction cannot be an atomic reaction. That's one problem. So new concept came that how we can make CH activation without Re-Functionalization. And actually that started long back, but now it really got good shape in last 2 decades. But it started long back, maybe 70 years back when Barton started first work on the CH functionalization. Now we come to compare this. Here, this position is unactivated, not functionalized anything, and we have an adjacent nitrogen group. Now this case is ideal. If we have a metal, then we can activate this position. So we add some palladium and we react with this aldehyde. What happens this? This carbon atom now binds with this carbon atom and forms this carbon-carbon bond. And if you look at, we analyze this reaction, what is the byproduct? What we lose? We lose only 1 molecule of hydrogen. So atomic economy in this reaction is very, very high. Atomic economy is very high, whereas in this reaction, atomic economy is not high. Not only atomic economy, if you look at this is atomic economic, step economic, and cost economic. Because here you have to make this material. And here you don't have that trouble of pre-functionalization. So step economy and cost economy, because you don't have the functionalization, all those things. So at one step, the CH activation and CH functionalization by activation is green by its concept of step economy, atomic economy, and cost economy, which are the basic features of any green synthesis or green parameters. Now real examples from my lab, from my works. There is CH nitration of arenes by palladium catalysis. Why nitro compounds? Nitro compounds are very important molecules. There are many molecules containing nitro groups are pharmaceutically important and are used in present drug. So these are some of the examples where you look, these compounds are very, very important compounds. Okay. So nitration is an important process. Now, how nitration is done? If you look at your textbook, you will find that classically nitration is done by using fuming nitric acid and sulfuric acid and high temperature, which is very, very hazardous. And later on, many methods came, and just a repetitive example here. That's a milder method, which is a reaction of aryl boronic acid with bismuth nitrate and other reagents. You can give nitration. But here also, the problem is you have to use some metallic nitrate, which is not very eco-friendly, rather toxic, and also you're losing this group. If you look at another example here, then you have to first lithiate, metallate here, and then they're treated with N2O4, which is also not so friendly, it's toxic. So in all these methods, either some metallic nitrate used, toxic compounds are used, and also the atomic economy is not that good. So what can be done on the context of CH activation? If you look at our example here, that's an azoarene, and we want to nitrate at this position. So use an organonitride, tertiary butyl nitride instead of metal nitride, because this is less toxic than metal nitride, and some palladium catalyst dioxide on this, and we can easily nitrate at this position. This position is nitrated now. That's what my title is, that unactivated CH, now we can make it this. They were unactivated as such. When you put a directing group, now we can activate this in presence of a metal, and you can then do the reaction with anything. I will show some examples here. It is nitration. We have many examples. If you look at this, all substituted, we have been substituted at different positions, like CF3, which is important pharmaceutically, and many methods. I mean, the yield is also fairly high. Okay, the unsymmetrical ajoarine. It's also for theoretical interest. If you look at this, this is an unsymmetrical ajoarine. One is this and is this. So, and here are two positions here. So, which can be nitrated, this position or this position? In this particular, this molecule, when we did this reaction under the same condition, we found the nitration only here. No nitration at this position. And that's because the steric hindrance by this group. Now, if we put a carbonyl group in between, then now this unit is now far away from this. So we are removing the steric hindrance of this position. And really we found that also in real result. Now nitration occurs here. This is a predominant position here and some nitration here also. So it's 23% for 56%. That's because of this removal of steric hindrance plus some activity of this carbonyl group. The mechanism, that's the usual mechanism of this is when you add some metal, that metal with this heteroatom forms a metallocycle, in this case palladicycle. This forms, first step is this formation of palladicycle. And then we have tertiary butyl nitrite, which under the reaction condition decomposes to give the generates the NO radical. This NO radical in presence of air forms nitro radical. And here this reaction does not go in absence of air. That's because of this step is crucial that you need air for conversion of nitric oxide, NO2, nitrogen oxide to nitrogen dioxide. This NO2 radical now interacts with this unit, forming this palladium 3 intermediate, which I have the evidence I will show in next slide. And this now undergoes again oxidation with air giving palladium 4 intermediate. And this by reductive elimination, you can get the compound and palladium back, and then you can close the cycle. And as I told you, that's a palladium 3, when you take the UV experiment, we found that in UV, after the initial stage, after the start of the reaction, we found a peak at UV at 445, which indicates palladium 3. So that supports the mechanism we showed earlier. Okay. Now we can see highlights of this reaction is really mild reaction conditions compared to the classical nitration, applicability to a wide range of diversely substituted ajoarines, excellent regioselectivity, and additive and external oxygen free and high yield of products. Okay. Another ajoarine. We have other many too, but just to give one example, that is nitration. Now we are getting this acylation. So the same ajoarine, if we use some acylating agent in palladium catalyst, we can get the acylation here. But if you look at this, instead of taking the normal acylating agent, we took alpha hydroxyketone or 1,2-diketone. So that's also very new for acylation. Not, I think 1 or 2 examples are there when we started the work, but still not many examples of using this thing. But we found that this compound, that alpha hydroxyketone or 1,2-diketone, can be used successfully for acylation reaction. Okay, we found many compounds. As you look at this, many substituted compounds here, substitution here, here. So all this shows the versatility of the method. And what is this here? That's the application of this protocol here. If we have an ajoarine here, you can acylate here. Then if you reduce it zinc ammonium trimethanol, you can get this compound. That's liver 10 receptor antagonist. That's the pharmaceutically important compound. And mechanism almost the same, nothing else. That palladium forms the cycle with palladicycle here. And then here, this alpha hydroxyketone is converted by TBHP, that's what hydrogen peroxide, to 1,2-diketone. This is undergoes cleavage here, forming this radical. And this radical now reacts with this intermediate, forming this compound, and which then under reductive elimination, you can get this compound and this. Okay. So here, this is also applicable to introduce acyl, heteroaryl, alkyl. Any kind of acyl group you can introduce. That's the versatility of this method. Applicable to wide range of diversely substituted ajoarines. It's excellent regioselectivity here also, high yield of products. And also we can use it for some bioactive molecules. So it has some application in the pharmaceutical industry. That's another important reaction here, whereas then there's the tandem cyanation and nitration, amination. That's a very important reaction. Both are very important groups, cyano and amino. And how this is classically done. Usually, if someone asks them how to make a cyanation and amination in a compound, usual method is that you have an iodobenzene, then you can make a metallate here, then you can make amination and then cyanation, or other way, first cyanation, then amination. So it takes 3 steps. Moreover, if you go to Buchwald-Hartwig, then also it takes 2 steps. And if you go to the Beller method, it can take 2 steps. So not less than 2 steps. But now, always there's now step economy. Everybody is talking about step economy and all the things. So how can we reduce the step? Okay. And we took the help of Catalan reaction. And here, the same compound, that's iodobenzene, and use it 1 step. Palladium, ligand is diphenylphosphine, norbornene, and this cyano reagent called potassium ferrocyanide that is introduced by Beller. And we found that here, there's in 1 step here, we can get amination and cyanation in 1 step. Not only that, if we can just modify the amount of the reagent, we can even wish amination and cyanation. So that's a very nice reaction that in 1 step, you can teach 2 important functional groups. Okay. Here also, the many examples of this monocyano amination. Here, many examples you'll find that all substituted. Which whenever we took some method, we make lots of substrates so that it shows the generality and the versatility of the method. If you look at this, all kinds of substitution here, NO2, OCF3, amine, CH3, and then OCH2PH, everything. So that anyone can use for the method for anything. Okay. And that's again the bisamination. The same method we can use for bisamination and cyanation. And we have many examples here. If you look at this, all the examples here, you can find it, and also yield is also considerably good. Okay. Now, this is a very real nice example. If you look at this, we have diiodobenzene. If you look at this part, we can have all 6 substituted benzene. That's a nice example that in 1 step, you can make all 6 substitution. 2 CC bond and 4 CN bond. Other way, 2 cyanation, 4 lamination. You find one example in literature where you can show me that there are many more examples of this type of thing, that in 1 step, you can induce 6 substituents in benzene. So that's a real and also a very good yield, 70% yield. If you look at this, 70% yield of the hex substitution in 1 step. So you can call it atom economy, step economy, time economy, cost economy, everything. So if you have to do the 6 molecules in step by step, so that's a really hell of a problem. But you can 1 step, you can make this molecule. Okay. Okay, yeah, we also found that in gram scale reaction also, we have 1.1 gram also, you can do the similar liquid good yield. And this is also some synthetic potential of this molecule, that we can make molecule in 1 step. And then in other 3 steps, you can make this molecule, this anti-HB reagents, that is hepatitis B virus agents. And there's a nice molecule, and we can make from this molecule in 3 steps. So our method can produce a precursor of these compounds. Okay. Mechanism looks like complex, but actually it's based on the same principle. Then we have the iodide which undergoes reaction with the palladium, and with the non-bonding, it forms this pallada cycle here, palladium 2, and then this oxidative addition with amine, you can get this molecule, the reductive elimination again, you can get this, and then non-bonding extrusion, you got this compound, this is one, and then cyanation, you can get this. So that's actually not very difficult, but because many steps are involved, that looks like there's a big complex mechanism, but it's based on the same principle of metallation and all the things. Another reaction is that. That is the olefination of that is benzoxagenone. So here, there's also again palladium catalyzed. And here also, if you look at a very interesting reaction, that we can olefinate at this position or there. Here are 3 potential positions here, which can be functionalized. And we put a tertiary, this is the activated alkene, that is tertiary butyl acrylate or methyl acrylate. You can find that this reaction occurs only at this position. And I will explain it because that's also puzzling for us. Then we took the help of theoretical calculation. And the end of this thing, I will show you that why we are getting the, olefination at this position only. If you look at this, okay, we have many examples. This is the actual condition and all the things. If you look at this tertiary butyl acrylate 5 equivalent and here, and if you look at this, you can get many molecules here with different substitutions here, all the things. And that's with the functionalized benzoxagenone, and here you can get that many substitution here at this molecule, Cl, and this OCH3, CF3, and that's again with butyl acrylate. Okay, this is the other one. Okay, you can also do it with methyl acrylate, the same reaction. This is not just an extension of this, nothing much on this. This is also substitution with methyl acrylate. Okay. Yeah, here also with, if you look at this molecule, this is the heteroadenine substitution, which sometimes is very challenging. But we found that our method is also suitable for heteroadenine substituted benzoxagenone method also, unit also. If you look at this, you can all the sorts of substitution we can make it. Yeah. If you look at this, you can also from that methyl, this position here also that we have meta substituted position. So here the question is whether it goes here or here. But we found that here also the reaction goes only at this position, not at this position. So all the exclusive reaction, we got it in this position only, the adjacent to this nitrogen. And we have the extra structure of this molecule so that it confirms the structure allotted for all these things by NMR and other things. Yeah. Now in the gram scale reaction, in the gram scale also you can get this molecule, so it has a scalability also. Now this is very important, really important thing. So what puzzled me from the beginning, that why it's having the functionalization at this only position. Okay. Here the activation through nitrogen. If it is at all, the activation through oxygen. And here the activation of this CO group. So we got considered the theoretical model of these things, where you look at this, this is the thing of this thing, and this is of this molecule, and we also this with nitrogen. Okay. So here we found that this molecule, this molecule is more stable than all these things. That is, this is C. C is 31.4 kilocalorie more stable than A, and C is 12.5 kilocalorie more than B. So now we can easily assume or easily understand that why we got the exclusive olefination at this position only, because this position, the corresponding metallocycle of this is more stable than the corresponding metallocycles of this. So this gives you answer. So for many molecules of CH activation, not only me, but other groups also, whenever they could not find out the reason that why is this, they can take the help of theoretical study, and they can find out that because of this energy stability and this, the reaction preferentially goes to one position. Okay, mechanism is almost the same, nothing new, because you have get this palladium acetate reaction with this and palladium cycle and this olefination at this position, and then you can reductive elimination. You can all mechanism almost the same thing. Yeah. So we can say that selective dehydrogenative olefination, wide functional group tolerance, regioselective is always found in this CH activation reaction. Always. There's applicability to heteroaryl benzoxagenone moiety and mild reaction. Okay, fine. This is very, very important. Okay. So far, what you have found that all the reactions I have mentioned is through palladium. And palladium occupies a very bigger space in CH activation reaction. So it started with palladium and still palladium is going. But palladium has some also disadvantages. One is that palladium salts, palladium complexes are very costly. Second is palladium is toxic. So then people are now thinking that whether we can get an alternative metal which will be less toxic and less expensive. So the people working in this area then looking for whether cobalt, nickel, copper or iron can be used for this. Iron is very challenging, but still there are some examples of using iron for CH activation. So that thing came that whether these metals can be used in place of palladium for this reaction. Okay, so this is another thing. So on that drive, we found that we can also make one reaction to cobalt. This reaction was done by cobalt, and actually after this study, we have not used palladium. Whatever we did after this, 2015, 16 onwards, 16, 17 onwards, so we always explored other metals other than palladium. It can be copper, I will show copper also, copper or cobalt or something else, okay? So here, one example of that is cobalt, okay? Another thing that, if you compare all other reactions, whatever I told so far, the reactions are carried out in higher temperature, 1000 or around 1000, 100 or around 100, like 90 or 110 or something like that. But all reactions are carried out in higher temperature, like 100 or so. So that also not satisfies the green parameter. So we have in mind that whether this reaction can be done in room temperature. That this reaction also satisfies that. Okay, fine. So, and for chemically, one is this is 8-aminoquinoline amide. Quinoline molecules are very important molecules. I will show in next slide that many drugs containing quinoline units are used in the market, commercial drug. So quinoline unit is functionalization of quinoline unit is very important. Okay, fine. And if you look at this, I don't know, this is not much visible, but this is a cyclic ether. I'm telling you, believe me, this is a cyclic ether, like tetrahydrofuran or so. So it is a cyclic ether. And where we are doing is this, we are alkylating here the cyclic ether. Okay. If you look at tetrahydrofuran, it's very inert. That's why I use a solvent. So functionalization of a molecule like tetrahydrofuran is also very challenging. So in this reaction, we made so many challenges. So functionalization of chemically, functionalization of tetrahydrofuran or cyclic ether. Another thing is that, again, so far in all of the examples I've shown, we found that CH functionalization occurs in the position adjacent to the heteroatom. Adjacent to the, if it is nitrogen here, adjacent means up with this CH or so, like proximity. At the proximity of the heteroatom, we got the activation. But here we look at this again. We are getting functionalization at this position, which is remote, at the fourth position from here, 1, 2, 3, 4. So that's a remote functionalization. So another characteristic is that this reaction, the remote functionalization of inert molecule like tetrahydrofuran, use of a metal other than palladium, reaction at room temperature, and with a CFL lamp or LED bulb, both. CFL lamp or LED bulb can be used for this activation. So that's a really nice, we are very much satisfied after this work, and we also did some other works also. But this is another milestone of our research, that we broke so many things which we did earlier. Okay, so this reaction is very good reaction, and I will come to more details here. Okay, and if you, as I told you that if you look containing the quinoline molecule, you find that chloroquine, medesamine, and medicosamine, and so primaquine. There are many molecules which contains this unit. And again, with the tetrahydrofuran unit, there are many molecules also containing the tetrahydrofuran derivatives, which are also pharmaceutically important. So both the molecules, both THF and this molecule are important. So that's why we took the quinoline moiety, and this moiety, we can take this, I think. Yeah. So now, after doing the reaction, when you just look at the literature, we found that The functionalization at this molecule is not new. But what I found that in this molecule earlier, all the functionalization occurred at the C5 position. At the C5 position, only except one example where they got C4 functionalization, the silver salt phosphorylation. As a phosphorylation, it got a different mechanism also. Okay, but in our case, we found that in all cases, we got exclusively C4 functionalization. Exclusively C4 functionalization of this. If you look at the molecule now and the product, we have C4 functionalization at this thing is a tetrahydrofuran or other cyclic ethers. So that's the thing that always you got this. And the real condition is that cobalt state Yoshinwa, you have this photosensitizer because you are using the CFL bulb, TBHP oxidizing agent, cesium carbonate, DMSO, 30 watt of CFL, normal CFL lamp, room temperature reaction 4 to 6 hours. Again, earlier palladium catalytic reactions in our cases also, the reaction takes longer time than 4 to 6 hours. So here we also broke the time that it's relatively less time, room temperature, use of inexpensive metal, cobalt, and all the things. We just made so many things. We made so many things to the challenge of so many things. Okay. Now, we got many molecules, as I told, that variation of amides. If we have that amide molecule, we change this R in different position. If you look at this position, here is different R, here is a different R. So heterodyne, and aliphatic, or aryl, norbornene, everywhere the reaction goes in relatively good yield. And also the ethers, not only THF, we got this ether, 6-membered ether, the dioxane, this is the dioxane, this is this molecule. So in acyclic ether, so everywhere the reaction is suitable. So that again, I saw the general applicability of this reaction. Okay. Now, missed one? No, it's okay. Okay. Now to find out the mechanism, we did some investigation and some control experiments investigation. When you do the radical quenching experiments, the normal experiment with tempo, everybody does this. So in tempo, with equivalent tempo, we found that we did not get, and the reaction is completely arrested, did not get any product. And we also got the tempo arrested compound, the tempo and the addition of tempo and tetrahydrofuran, this compound. We have isolated this compound, took the NMR and all that things, characterized it. Okay. So this shows the reaction is going by a radical experiment or radical process. Fine. Then we did a kinetic isotope experiment. And here you also find that KH by KD is 3.1721, which indicates that the proton abstraction or the formation of radical from this, if it is, this is the rate determining step. So KH by KD indicates that the proton abstraction is the rate determining step. Okay. Next question. We found another article in Oglate in 2015 that they also calculate the charge distribution of this molecule at this C2, C4, C5, C7. And by natural charge distribution and PZ orbital occupancy calculation. What they have found that the C5 and C7 may be the most likely electrophilic reactive site. And whereas C2 and C4 is the most nucleophilic reactive site, that is electron deficient. In other words, these two positions are relatively electron deficient than these two positions of C5 and C7. Okay. Now we are getting the radical from, say, tetrahydrofuran or cyclic ether. That's the carbanion. That's the carbon center radicals are nucleophilic nature. So that's the tiny nucleophile. So that tiny nucleophile now naturally prefers to attack at C2 or C4, that is less electron deficient compared to this. But C2 has some steric hindrance and C4 is free. So naturally the reaction goes exclusively at C4 and we got C4 substituted product. We are also happy that this paper helps us, this paper really helps us to find out the real cause of this C4 substitution. Okay. Now the mechanism is almost the same again. With cobalt metal, this forms this metal cycle. At the same time, with tertiary butyl hydrogen peroxide, it gives tertiary butyl radical with photoactivated eosin Y. And then tertiary butyl radical then abstracts hydrogen from, excuse me, and forms this radical here. This radical now reacts with this, giving this radical, and this reaction reacts with photoactivated eosin cationic radical from this positively charged species, which then generates this molecule, that's the real product, and generates the catalyst. So the cycle goes like this. Okay. So actually what I already explained this is a cobalt catalyzed selective remote stiffer. This is called remote stiffer functionalization of 8 amino quinolamides. This is under simple irradiation with CFL lamp at room temperature, using chief environmentally friendly eosin as photocatalyst, broad substrate scopes, many compound, and we also happy with mechanistic investigation, kinetic study. Okay. Now we are coming to another example. Again, this is with copper. That's also very interesting. That's the cobalt, that's the copper. And now what it did here, the same molecule, 8 amino quinolamide, and we are doing here amidation. But that's also very novel way that we are using an acyl azide. Use of acyl azide for amidation also new. No one has done it. So use of acyl azide for amidation. And what is more interesting is this molecule 8 amino quinolamide, when you arrive normal benzoyl azide with copper acetate, 1.2 equivalent room temperature, we can get the normal expected product, that alloyl amidation. Fine. But very interestingly, when we increase the equivalent of copper acetate to 2 equivalent, actually that was accidental. Someone used it at a little bit more of that, and we observed a new observation here, that is the acetyl amidation. Look at this. Synthetically, you can make alloyl amidation or acetyl amidation just with the increase of modifying the amount of copper acetate of the catalyst. Nothing else. Everything remains the same. Only if you use copper acetate 2 equivalent, you get acetyl amidation. Is 1.2 equivalent or 1 equivalent, you can get alloyl amidation. So whatever the reason is, we'll come to the reason. But whatever the reason is, the reaction is naturally very interesting for any synthetic organic chemist. Okay, let us look at the synthesis. We have got many molecules in that. When you use 1.2 equivalent, the major compound is this normal expected alloyl amidation. You look at the many molecules here, all of the very high yield and all substituted, differently substituted. Then we come to this 2 equivalent. Then we got the major compound is acetylamide. Acetylamide, and minor is very this. So you have many, it's not a simple one example, isolated example, or just go, happened one. It's a very general reaction. It's a very general reaction that when you use the copper acetate 1 equivalent, you got the alloyl amidation. And when you use 2 equivalent, you got the acetyl amidation. Acetyl, I'm making acetyl, not acyl. Acetyl amidation. That's the really interesting, and it's a very, very general reaction. But what is that? Yeah, this reason. Well, naturally, we'll find it. Okay. So that puzzled us also, and that find out interesting also, that how we can find the solution or reason for it. Yeah. We did some contour experiments. Just listen carefully. First thing we did, that there is 8 amino quinolamide, and we just known acetyl azide. We took the react from the known acetyl azide, and we found that yes, amidation, acetyl amidation occurs. So that gives us a clue, something that maybe in some way that acetyl azide is formed in the reaction. Now how? That's the $1 million question. How that acetyl azide is formed in the reaction? Okay. Then we did another experiment. We took benzoyl azide, and then we used the same way, copper acetate 2 equivalent, potassium carbonate, all these things same. And we found that really, to our surprise, we got acetyl azide here, it detected by HRMS, then also by analysis and big way. So we find that acetyl azide itself is being formed from benzoyl azide in presence of two equivalent copper acetate. Now the question, how come this acetyl moiety comes? Where it is coming from? Only source we use is copper acetate. So anybody can guess that it is coming from copper acetate. Then you look at the literature and we found that really copper acetate and other metal acetates can transfer OAC to other molecules. So now we found that when you use the two equivalent to copper acetate, that time rather than doing the reaction, this acetate molecule interacts with this and forms this acetyl azide. Okay. Now when this forms this, we did another experiment. The normal reaction, that is 8-aminoquinol benzamide, we took aryl azide, benzoyl azide, and acyl azide. And here we found that most of the product, 58% product, is formed from acetyl azide. So it's coming from this and coming from this also. And the trace amount of this. That means, again, it proves that when you use two equivalent this reaction is favorable. That this converts to acetyl azide, which then undergoes the reaction to give this acetyl amidation. Okay, so we solve this mystery that how it coming and all the things. Mechanism is the same. Mechanism we are not worried about. That copper again forms the metal cycle, copper cycle with this, and this is also directed by HRMS analysis, and then it reacts with acyl azide forming this. Then you can exclusion of nitrogen, you can get this molecule, and then exclusion of this metal molecule, like normal mechanism, you can get this compound and copper metal and goes the cycle. And then you form the same thing, that you can repeat the thing with acetyl azide formed from aryl azide. So mechanism is nothing new or nothing this, it's all the same. Okay. Now we showed if the palladium catalytic activation, copper catalytic activation, cobalt catalytic activation. And also with light, visible light catalyzed activation, like in cobalt case. Now, another thing we can, that's mechanically induced activation. That's also very new. That's CH activation by ball milling. And first example was given by Kastenbaum, which is published, I think, 2017 or so in Angu. And then it was coming now. It is now coming the mechanically induced alkylation, mechanically induced activation can also be done without using any metal. Okay. And okay, the title is the bicyclic arenes, chalcogenation of bicyclic arenes. Why bicyclic arenes? These bicyclic arenes are also pharmaceutically very important. If you look at this, many molecules, that's bicyclic arenes, molecules containing other substituents, the selenide and all the things. If you look at this, bicyclic and selenides, and here. So all these molecules are also very important. Okay. Now, if you look at this reaction here, the simple molecule beta-naphthol, substituted beta-naphthol here. And this molecule, if you take a diaryl or diphenyl disulfide or selenide, basic alumina washed with KOH, the basic alumina, in ball milling 600 RPM with 5 balls 1 hour, you can get selenation here. And again, you look at the unactivated CH, that is unfunctionalized, not pre-functionalized, unfunctionalized CH, you can get sulfonation here. And here also we don't need any metal. So without using any metal, without using an oxidant, without using a high temperature, and that's the ambient temperature 40 degrees or so, in 1 hour, you can get the selenation at this position, selenium sulfonation here. You can get a diaryl disulfide selenide, or you can get other selenide reagent like aryl selenocyanate or aryl selenium halide. You can get the same product with this. Okay. There are many examples here. If you look at diphenyl diselenide, the basic alumina, you can get this compound, and with different substitution, the yield is very, very high in all the cases. Actually, in ball milling reaction to our experience, we found that yield is usually high, less side product, and also very mild condition. That we did many, other lectures we give in ball milling. I think even in Akal University also gave other conference I get the lecture by ball milling. That time I thought that I will give something else. Okay. Here also, if you find that yes, with substituted thing, we can get many molecules here. All these molecules are very important pharmaceutically. And also we took the X-ray of these compounds, where we found that it's really finally corresponds to the molecule we assign from the spectroscopy and this. So that's a very nice thing. Okay, if you use other reagent like cyanate, we can get also the selenation, the binary selenation compound and this, many molecules. Okay, here also selenium halide, we can put the same molecule. So it has an opportunity to use many other reagents, not only diphenyl, diselenate or disulfide, we can get all the things. Yeah. Okay. Whenever I did the reaction, but almost all the reaction in synthetic, in our synthetic methods, we always try the gram scale reaction. And also whenever we try some, whether that can be used for some material formation or some pharmaceutical importance or so. So whether it works or not. That's a routine instruction in our lab. So in gram scale synthesis also it's very good. That's normal, not the yield is very less. So it can be scalability. And now for the mechanism thing, when you reaction tempo, we found that no reaction arresting. So it's almost the same. So it's not going by radical process. So the reaction pathway possibly this now, this is under the ball milling and this we can form the anion and this activated this position like this. If you have a Na here, we use a KOH here. So we have some metal here and undergoes this sometimes cycle here with selenium and this. So it's activated at this position and then we get selenation and the normal aromatization, you can get this. Okay. So we call this is a mechanochemically chalcogenation of bicyclic. There's a mechanochemically chalcogenation that is inexpensive 2-naphthol as starting material. It's a large functional group tolerance. We can get many. That's another important thing of ball milling and visible light catalyzed that usually it does not affect the functional group. Both the process so mild that whether you have ester or tosylate or silicate or some silide or anything, usually they are not affected by ball milling and visible light photocatalyzed reaction. That's another thing, that's general thing. And actually this takes a metal, oxygen and base free. So that's another really thing because pharmaceutical industry then does not tolerate use of metal because metal contamination is very dangerous and also oxidant also is not very good. So this reaction is on the way very mild without using any metal and oxidant, all the things. Yeah. So I think that's all I think. Okay. The technical thing. Okay. I am in the time, little earlier time. Okay. They are the people who worked in this field, the Sabir, Devashish, Pintu, Biju, Dubai and Subir. All are, no one is here in my love. But anyway, all are established and doing their job. And also for funds, Indian National Science Academy giving me Indian, it's a senior scientist and then in honorary scientist. My Jeshivas fellowship for 10 years. That's also very lump sum money. And my institute, Indian Association for the Cultivation of Science. And here are some of the pictures of our group and light moments, many times in many places. Okay, and thank you. And that's obviously that's our institute, Indian Association of Cultivation Science. Those who have not, visited, this is for them. That's a very nice building and nice ambience. It's eco-friendly, and well, thank you all.
Thank you so much, sir. Thank you for your very informative and valuable lecture. As usual, this is the 4th time I am listening to your lecture, and every time it is something new. So thank you so much, sir, and thank you so much. I think our participants have enjoyed your lecture and learned many things about CH activation, and by using CH activation, how you synthesize different scaffolds and different even some heterocycles also. So now I'm requesting as Professor Angelo Di Fatima, our last speaker of the day, is also present. So still you have 9 minutes. So dear participants, if you have any questions or or otherwise you can share your views with Professor Ranu. This is a great opportunity for all of you. You can directly interact with you, sir. So I'm requesting some international participants like Helena Palliser. Can you please unmute yourself and share your views? Helena, can you please unmute and share your views? Helena Palliser, can you please unmute and share your views? or any other? Daniel, can you please? Okay, so any other participants who want to interact with sir, please raise your hand or we will make you unmute, give you permission, record permission so that you can interact with sir. Any other participants? Huh? Huh?
Yes. Aditi Singh raised hand. Boon.
Yes.
Yes, sir. Sir, am I audible?
Yeah,
Yes, you are very much audible.
Yeah,
please start your
yeah,
video.
yeah, sir. Sir, good, sir. Yeah, good evening, sir. Sir,
Good evening.
first of all, sir, really
Aditi,
very.
please start your video as well.
Yeah, sir. So actually, I am in this. I will start. Sir. Actually, I'm in lab. That's why I'll start. So first of all, sir, I'm really grateful that I've gotten this opportunity to be a part of this workshop. And since morning I'm attending it and I have found it. So just a moment, I'll start my video. Just a moment. Yes, sir. Am I visible?
Yes, visible, yeah. Do you have any question? Okay, go ahead.
So good evening, sir.
Yes.
Yes, sir. I am at hostel. I am a hostel. Right. Yeah.
Go ahead.
Yeah.
If you have any question?
Sir, I want to say that, no, sir, I have no question. I'm really grateful that I've been a part of this. And thank you so much for conducting this. And I'm looking forward for other 2 sessions as well, sir. Thank you so much, sir. I have no questions, sir.
Thank you,
Okay.
sir. Nidjar sir.
Vimal looks like you have some question.
Sir, yeah, Nidjar sir wrote one question. Was the nitration was done using oxygen balloon or oxygen bubbling or normal aerial oxygen?
Normal aerial oxygen, just normal open atmosphere.
Okay, sir. So, dear participants, please, if you have still there are 3-4 minutes, so you can.
Professor Bonik, do you have any question? Unmute. Okay, Bimal, you have to unmute. Bimal, we cannot hear you. You can unmute.
Bimal sir. Bimal sir. Bimal.
It looks like he wants to tell something, but he's okay. Anyway, someone raised hand. Okay. It's okay?
Yeah, now Bimal sir.
Yes. Go ahead, Bimal.
It was blocked. One section was blocked.
What?
You have done iodobenzene to cyanobenzene.
Yes.
What about other halide like bromine, chlorine? They also participate in the same way.
Yeah. Not chloride. Bromide, iodide works in the same way. Chloride is in chlorine case.
Same way, bromide, iodide. Not
Yield is
chloride.
less. Yield is less. Yes. But that's the tandem. I mean, you can say the cyanation, amination in one step. That's that reaction.
So that was my question.
Yeah. Okay. Thank you.
Thank you. Thank you.
Thank you, Bimal sir. Thank you, Professor Ranu. Now, any other participants? Please, still there are 2-3 minutes. So, if you want to still interact with sir, yeah, Dr. Prashant, Dr. Nidhi Goel, Dr. Navjeet Kaur Madam, Dr. Sunita, if you want, Dr. Neeraj, Dr. Vijay.
Hello, sir.
Yes.
Am I audible, sir?
Yes, yes.
Yes, sir. I have a question. Can we replace that K2S2O8 catalyst, one of the coupling reaction that you have used?
Yes, I think you mean that that cobalt catalyzed reaction, right?
Yes, sir. Yes, sir. Right.
Yeah. I think you can use that's an oxidizing agent, so you can use, I think, but we have not tried. But you can. I know. Yes.
Okay. Means why I asked is that means in some of the reactions you have used K2CO, there is a K2CO3, potassium carbonate. Potassium carbonate.
Yes, potassium carbonate.
As I am a green chemist, that I can get K2CO3 as a catalyst from some of the various agro-waste derived catalysts. So I have also tried them, and I have prepared their waste extract, and I have means ongoing some that affiliation reactions using agro-waste catalyst. So exactly in the same way as my catalyst will work as an organic base.
Yeah, K2CO3. Yeah, go ahead. K2CO3 is a good base. Yes. Go ahead.
Yes. So how actually means K2CO3 is acting as a base, sir. So as a K2S2O8, how it is acting as a base or as a mild acid?
No, K2S2.
What is the role of that catalyst?
Yes, no. Yeah. That's actually act like the mild oxidizing agent, and K2CO3 is a base. Okay.
Yes, sir. Okay. Okay, sir. Thank you, sir. It was really very informative. Thank you very much.
Thank you.
Thank you.
I'm now requesting Dr. Arunabho Agarwal, sir. Arunabho Agarwal, sir, can you please? Yes, sir. Can you please share your views?
Okay, can you hear me?
Yes, I can.
Okay, so I am from Malda College, and my specialization is inorganic chemistry. So all reactions are new. So I learned something new about that. Some organic reaction. I did my PhD in inorganic chemistry.
Yes,
so
all are same. Yes, okay.
Yeah. So it was nice. Morning, it was nice. All lectures are nice. Thank you.
Okay, thank you. Do something in Malda College. Try to do something. Okay?
Yes, sir.
Okay.
Yes, sir.
Thank you so much, sir. Thank you so much.
Somebody Nidjor Shaha, I think raised hand.
Yes.
Okay, Nidjor, go ahead. Nidjor, can you hear me? You can ask your question.
Sir, can you hear me?
Yes, I can.
Sir, my question is that as you also do reactions with ball milling approach, so is the metal catalyzed CH activation can be done through ball milling approach, especially following the CMD pathway?
Actually, this research is really very intense now that people are trying that without using metal, whether only ball milling can do that. Particularly that reaction can be done, but those reactions which I showed earlier, whether that can be done without metal is still a challenge. Still a challenge. But custom dome interviews, that's also in space of metal. Yeah, that's still a challenge.
Okay, sir. And my next question is that is arising in my mind from various times. That is, can we call Hake cross coupling a CH activation approach?
No. This is not Hake coupling or this is not CH activation. That's a coupling reaction.
Okay.
Not activation. I mean, okay, activation is a very general term. I mean, it's a very broad term that whenever you activate how and this, but whatever now is what is CH activation now is called that with the metal or same metal through metal or cycle. So Hake coupling cannot be called in that way.
Okay, sir.
Yeah, but any reaction, as I told you in the first slide, that any reaction you have to activate the particular position to make it to react. Okay, that's the basic question of organic synthetic organic chemistry.
Okay, sir. Thank you, sir.
So yeah, Deblina, you have any question or you want to share your views?
Yes, good afternoon, everyone. And thanks to Professor Ranu. It was a great lecture. I have one question is that, first of all, it's like, what are the general challenges associated with each of these siege activations?
Can you be louder? I mean, I cannot get you properly. Devlina?
Hello, am I audible?
Yeah, you're
Is it
audible,
fine?
but the part I cannot hear. Anyway.
Okay, okay. It's better now?
Yes.
You can start your video as well.
No, it will drop. Actually, there is
Okay, go
some
ahead.
issue with
Okay, put
internet.
your
That's
question.
why I'm okay. So, what are the associated challenges with siege activation? General challenges for
Yes.
siege activation.
Yes.
Yeah.
Yeah, general,
Yes.
that's your question?
Yes. Yes. Yes.
Okay. The general challenges of stage activation is that, as I told him in the cobalt reaction, that you can have to do it with the inexpensive metal. You have to do with non-toxic metal. You can do it at room temperature. You can do it, make it generalized. And also you can do the remote functionalization at your desire. But whatever you want, you can do that. If you can do that in that way, that the room temperature reaction and that's this, all these things will be very, very good. That's the real challenges. Because most of the activation reactions are done in high temperature, which is not acceptable in the perspective of green chemistry. Okay.
During the reaction, what challenges, what difficulties generally you can face, as you think to face? Is it differing? Is it differing reaction to reaction? Like for some reactions, we face some difficulty while we carry out the reaction. So, is there some difficulties generally we face in CH activation while doing the reaction?
Yeah, one thing is that the CH activation does not need pre-functionalization. That's another advantage. So we have to use this thing, and this is now CH activation in a large way.
Okay, suppose if directing group is there and we need to activate the ortho position related to that, will there be any scope that double activation can take place and we get like double activated product in both of the position where it's free?
Yes, go ahead.
Yes, I'm telling that if we have a like a protecting group or we have a like directing group, not a protecting group, it's directing group. So if we want to do the ortho activation and if the other ortho position is also vacant, so is there any difunctionalization that happens?
Yeah, one thing, very good question. Also, I also showed it that from energy calculation or so, that which position will be activated. So where the possibility of this metal formation and metal cycle is more, that is be the most vulnerable position. It will react there. But if there is some other possibility there, it can be bis. And I showed one example in my lecture also. It's of products. It can be.
Yes.
But the question is, you can tune it. You can tune it by appropriate functionality, that you can tune it to get the reaction in a particular position. That is the challenge.
Yes, yes.
That's the chemist can do it.
Yeah. And second question is for the hydroxy group in naphthol, what you have shown, it's the ortho substitution or ortho functionalization that is there, right? For selenylation, the last one. So in that case, if we use the phenol kind of derivatives, is it ortho or para?
Yeah, it's not actually, it's not applicable for phenol. That's the only beta naphthol. But where
that has been done here.
Yes. Right. Actually.
Yes. But any example tried with phenol kind of substrate?
Yeah, if it is substituted phenol, I think that can be done. It's not a real. I don't think out the thing. You can have it.
Yeah, but because sometimes it's a mixture where para is there and ortho is there also as a product. So that might be a challenge, I suppose.
Yeah.
Okay, thank you.
Thank you.
Professor Ranu, Professor Ranu, I found another question for you. If you don't mind, can you give me answer?
It's always a pleasure to have question from you.
Yes, Professor Ranu always helped me in giving me answers. Okay. You have done a lot of work, I see, on azo derivative, azo compound. Instead of azo, if you take similar activating group, do you think the same thing will happen or there is a possibility?
Yeah, definitely. Yes, okay. When you started the work in 2013-14, that's why the nitrogen is very tough. But that after, so, okay, I'm telling you, when the subject progresses, now people are trying sulfur, people are trying phosphorus, people are trying lots of things. Now, if you look at the you can do activation with sulfur, phosphorus, oxygen, anything with a different condition, not in the same condition what you use for nitrogen. Yes, in the last of my day, I mean in my group also, we did some reaction with phosphorus, even with phosphorus, and one of my students is now continuing. I mean now I retired, but now my student is continuing with sulfur and phosphorus. Yeah, that's the challenge, but you can do that. You can activate because nitrogen activated, but you can other groups are directing groups. Yeah. Now this subject has now expanded a lot now, so you can have yes.
Okay. Thank you.
Sure.
Thank you.
Okay, but I love this subject, the siege activation when it started, and now I love this subject. Yeah.
Thank you so much, sir. Thank you, Bimal sir. Thank you, Professor Ranu. Now our next speaker, Professor Angelo Di Fatima sir, is waiting. And so thank you so much once again, Ranu sir.
Yes, yes.
Now, Fatima sir, can you please unmute your mic and start your video? We have made you the co-host. Can you please start your video? Yes.
Can you hear me?
Yeah, yes, sir. Yes, sir. Thank you so much. Thank you, and very good morning to you. Because
yes.
So thank you so much for giving us this opportunity, and you have agreed to provide your valuable lecture for our participants. So thank you so much. So dear participants, let me introduce Professor Angelo Fatima sir. Sir did his bachelor degree in chemistry from the Federal University of Bicester 1990 and master degree in organic chemistry in 2002 and doctor in science in 2005 and postdoctor in biochemistry signal transduction in 2006 from State University of Campinas, and he has published several research papers and he received so many research awards, and he has supervised 15 master dissertation and 8 PhD theses and 6 postdoctoral intermediates and 10 course conclusion work, and he has organized several such regional and national and international and science events, and so he has published so many research articles with high impacted journals like Journal of Advanced Research and many other internationally reputed journals. His research direction is synthesis of total synthesis of natural products and analogs with pharmacologically interested or active scaffolds and various biologically relevant scaffolds. So with this short introduction, because already 10 minutes, it is now 4:10. So now over to you, sir. You please, you have already shared your screen, so your slides. So you please start your lecture. Thank you so much, sir.
Okay, thank you, Boom. I want to ask you to let me know if the sound and the image are okay, because
yes, sir. You are completely, you are audible, and your slides is visible also. Thank you so much.
Okay. First of all, I want to thank the organized committee for this opportunity, and I want to congratulate all previous speakers because I saw very nice chemistry and very nice, interesting molecules. Okay, today I'm gonna talk about some research that we are doing in Brazil in my research group, where we are using calixarine as a catalyst for some reactions. Okay, the outline of my lecture is I will do only one definition, what is calixarine. I will present 3 examples that we are using calixarine to synthesize duolidines, quinolines, and bignelli adducts and xantinones. In the end, I want to present a property of calixarine that is not related with catalysis, but is a very nice experiment how we can use calixarine to develop anti-cocaine vaccine, and then the conclusions. Okay, calixarine, the term calixarine was suggested by David Gutt in 1970. And this word means, the calyx means the vase, because one conformer of this such macrocycle remembers a vase. And a ring stands for the aromatic rings that is part of this macrocycle. You can produce different calixarines with different size, as I'm showing here, with 4 phenolic units, 6, 8, and you can prepare until 20 phenolic units. For do that, you can start from a very cheap materials like formaldehyde, this para-terpbutyl phenol. They are very inexpensive, and you can do this in microgram and gram scale. Why it is interesting to use calixarine as a catalyst? As I told you, because it's easy to prepare and cheaply, so you can prepare multigrams of this. You can modify the primary structure. You can incorporate chirality, so you can perform enantioselective or just stereoselective reactions. You can use the cavity of these macrocycles to recognize substrates, could be a molecule, an ion. Calixarine has a multiply bind sites, so you can use this advantage. You can fix in the solid support to get heterogeneous catalyst. There are several examples in the reactions that you can use calixarine. This is a Chem review published in 2008. You can see that calixarine 4 is the most used calixarine. Here I bring some examples. A manic type reaction, you can use calixarine 10 mol%. You can synthesize pyridines, use calixarines. You can do this reaction in an enantioselective way. In this case, the author described 69% of EE. And it is interesting when they compare the microcycle with the monomer, the chiral monomer, and the level of enantioselective was higher when they used the microcycle. So let us see our first example that we have working here in Brazil. We are interested in these 2 kind of molecules. Professor Ranu present a very nice quinolines derivatives, and we are also interested in this class of substance, duolidines and quinolines. Why duolidines? Because this moiety is present in several organic dyes for disolar cells. So we are interested to obtain this kind of molecules. There are several methods described in the literature to obtain this kind of molecules. One of them we have choose is from Mellor group. they have used trifluoric acetic acid as a catalyst, and they obtain these two Joule-Lawton derivatives. By using his condition in our reaction, a multi-component reaction, we have obtained 4B in 65% yield. So we start to use, when we use calixarine 4, the same solvent, we got less amount, but this compound, but when we change the solvent, when we use different solvent, and for our surprise, water was the best, we got the same yield of under the mellow condition. By decrease the amount of the calixarine, we got the same amount, but less, only 2% of the calixarine. And when you use 1 hour more, we got 70%. So we optimize our condition for this reaction, and we got a very nice yield for B. We have tried different acidic catalysts like sulfuric acid, but calixarine was better. One advantage of the for using calixarine, as these catalysts are solid, different from sulfuric acid, for example. They are air stable. You can produce in multi-gram quantities, and when you compare, for example, the monomer, as you can see here, this is the calixarine, this PHSA is a kind of a monomer of the microcycle. The yield is very low. So under the optimized condition, we have tried to use different amines, and we got all derivatives and good yields from 64 to 89%. We can also use different aldehyde in this reaction, but when we try benzaldehyde, for example, we failed into obtain 4B. What we observed was the quinoline and the imine. And the quinoline, the quantity of the quinoline, it was only 5%, a very low yield. This is sad, this is okay, we are going to give up. No, this is an opportunity. And because quinoline is a very privileged moiety you can find in different kind of substance of medicinal, agricultural interest. So we decided to explore a little bit more this condition. In the previous condition, using water, we got the quinoline in low yield, but when we remove water, do this reaction without water, the yield was higher, much higher. So we did some improvements. We increased the amount of the catalyst, is almost the same yield. We decreased the temperature of the reaction, but the best condition was to use 1 millimole of the catalyst under microwave irradiation, 20 minutes, and solvent-free. So we evaluate different aldehyde. We got these very nice quinoline derivatives. We change also the amine that we have used in this reaction. We got a very nice quinolines derivatives. So this was the first example. when that I have shown that we can use calixarine to obtain julolidine and quinolines, and by change the reaction condition, you can access julolidines or quinolines in different ways. Okay, my second example will be maybe the longest one, is about Bignell adults. And for Bignell adults are compounds that bears this moiety here. You can have oxygen or sulfur in this position. And we use also calixarine to obtain this kind of molecules. Here I'm showing the reaction that we have tried to use different calixarine, bearing here alkyl group, hydrogen, also sulfonic acid group here in this position. And without the catalyst under our condition, we obtain this Bignell adduct in only 12% of yield. And the best catalyst was again the acid one. The yields were up to 81% of yield. We can also use the monomer. The yields was slightly lower than the microcycle. And we have chose this calixarine to perform further studies. So we have used urea as a substrate and different aldehydes, aromatic aldehydes. You can get the adducts, the Bignell adducts, from 56 to 92% of yield. Alkyl aldehyde is not good substrate for such reaction. And you can also use thiourea as a substrate. The yields come from 49 to 83%. And you can also reuse the catalyst. And how you can do this, how we do this, you can add water in the reaction mixture. So the catalyst goes to the water phase, and you can wash the water phase with organic solvent to remove some reagents that remain the phase water. And you can evaporate water and use the residue in the next reaction. And as you can see here, you got the same efficacy in this reaction. But the student have told me, this is hard to do, the quenching of this reaction. Okay, we can think a better way. Anyone have an idea? I ask them. Okay, it's time to improve this part of our process. And we have to do some magnetic nanoparticle where you can bound our calixarine, our catalyst. So we prepared the calixarine, our catalyst. We have prepared the nanoparticles and modified this nanoparticle in order to get in their surface our catalyst. So you have prepared this material. And we use this material in this reaction, is the model reaction, and to prepare this Bignell adduct. What under this condition, 0.64 mole% of this material, microwave irradiation, this temperature 20 minutes. In order to show how it's work, we have prepared a video here. I hope this will work. Let me try it. As you can see here, our catalyst is here. You can do this dispersion of the material in the reaction medium. And when you check that the reaction is done, you can use a magnet to remove the catalyst. You can take out the reaction mixture and add again a new quantity of the reagents and perform the reaction. Of course, this video does not bring the microwave irradiation because we do this in microreactor, okay? But you can we try at least 5 cycles of reuse of this material in such reaction. The result and also the characterization of such material was published in this journal. If anyone want to know more details about it, you can check here. Okay, but as I told you, why we are interested in this kind of molecules? Because the bigenial adduct is structurally related with urea. And urea is one of the most used nitrogen fertilizer in agriculture. Here in Brazil, this is true. We need to import a million of tons of urea to use in the agriculture. But why of this? Because urea has some advantage over other end source, like it has high end content, low price, and easy to manage. It's a very easy to manage. For example, in Brazil, we have urea represent in 2017 almost 4% of all nitrogen fertilizer used here in Brazil. It's almost 5.6 million of tons. And all this quantity, 25% were imported. However, there is a drawback by using urea. Here in Brazil, the main drawback is urease. Urease is a hydrolyzed enzyme present in the soil, and this enzyme speed up the hydrolysis of urea in almost 100 trillion fold. So when you use urea in the agriculture, there are an enzyme in the soil that decrease the amount of nitrogen that will be available to the plant. So you lose fertilizer, and this hydrolysis convert urea into ammonia, and ammonia can go to nitrate that leach, and you have a problem of eutrophilization. This nitrogen can be oxidized and go to our atmosphere as well, ammonia. So we have also here environmental problem when you use urea as a fertilizer. This is a problem, I don't know, for us, this is an opportunity because you can use urease inhibitor to decrease the hydrolysis of urea. So from the agricultural point of view, soil urease activity must be modulated. We don't want to inhibit 100% of the activity. We need that urea be converted into ammonia because plant can take this ammonia as an end source, but not in the surface of the soil, but in rhizosphere of the plant. Urease is also a relevant virulence factor of H. pylori. And this urease turn Helicobacter pylori an effective infectant agent in the stomach. And this urease is so important that urease can represent up to 10% of the total protein content and H. pylori. Another very interesting information in the world, 2 from 3 people is infected with H. pylori. I got positive results about H. pylori. I have H. pylori, but in my case, it's not a big deal until now. But I decided to eliminate it, not by consuming my compounds, okay? By consume some drugs that are effective to that. Okay, are bigenyl adduct urease inhibitors? Well, they are at least chemically structurally related with thiourea, that it is a urease inhibitors. And when you look to the nature, those natural compounds that are known to be urease inhibitors, what we have noticed is many of them has a phenolic moiety on it. And we find this compound a very simple compound that has a nice urease inhibitor properties, methylgalate. So we decide to use some aldehyde, natural derived aldehydes that we can use to construct, to synthesize some bigenyl adducted as a potential urease inhibitors. When we evaluate the phenolic aldehyde against urease, we notice that only the protocatecute aldehyde was effective, not effective as our positive control, hydroxyurea, but very promising results. And the acetaldehyde and vanillin was not so effective. Again, this is a sad result. No, this is an opportunity, because what we intend to do is to convert those aldehydes to bigenyl adducts that are more similar to the thiourea, one of the well-known inhibitors. This was our plan, to obtain this kind of derivative that bears the thiourea moiety and also some phenolic groups. And what we have got, as you can see here, hydroxyurea was our positive control. This is the protocatecute aldehyde. It was the most promising aldehyde that we had. But look, our derivative, it's possess higher inhibitory effect. And this is more impressive. The vanillin was almost inactive. Now, the bigenyl adduct 2D2 has a 6% of inhibitory activity, as such as the acetaldehyde derivative. All previous results that I have shown is related with the in vitro assays. But what we intend to do is to obtain an effective compound in soil, and different from the in vitro reaction medium, soil is a very complex matrix. So we check the efficacy of the synthesized compounds in soil, and we have used a commercial available urease inhibitors, NBPT. NBPT is here, the results, and as you can see, derivatives 2A7 and 2D2 are as effective as the positive control. This was a very nice result that we have obtaining, because when NBPT is not a stable molecule, it's to obtain this compound, you produce a lot of undesirable subproducts. It is not NBPT. It is not stable. You cannot use NBPT to gather other nutrient source for plants, for example, phosphate. And our compounds are air stable. You can produce this in large amount, and we were very happy to obtain this kind of results. And we got further. We incorporate our product in urea. This is urea without our any urease inhibitor. This is urea with our inhibitor, and we participate of a competition in America Latin from idea to product, and we got the second place. Here are our compounds in an experiment using millet as a model. As you can see here, the fertilizer is important to the plant. Urea was used here. Here is urea free. And here, urea plus our inhibitor in different amount. For this work, we earned the Corte Technology Award that was a part of the was given to us for the Brazilian Chemical Industry Association, and this prize was given to us by the former president of Brazil, Michel Temer, in that occasion. So we can use natural phenolic aldehydes and hybridize this compound with thiourea. This is our hybrid. It's a known compound, but was designed based that thiourea is a urease inhibitors. We need to have, we have improved the anti-ureolytic activity by bearing here some phenolic units. We have tried a different kind of Viginelli adducts. We test almost 45 compounds, and we all, and from this total of compound, we noticed that this phenolic unit is very important for the activity. And these results are from efforts from network for the development of novel urease inhibitors. Is a national network that I am the coordinator of this national network, and we are open for collaborations, to talk, to test compounds. All of you are welcome to contribute with this national, maybe turn it an international network to development of novel urease inhibitors. From the both point of view, the medicinal and also the agricultural. Okay, the third example is xanthanones. Xanthanones is a very interesting molecule that you can find in different, here all of these compounds are natural compounds that possess a very nice biological activity, anti-cancer activity, anti-plasmodium activity, And we decide to use a multi-component approach to obtain different kind of xanthonones and test them against cancer cells. So again, we have tested all calixarin that we have worked so far. And we saw the same behavior. Without catalyst, the yield is lower, but by using calixarins, you can improve this yield in a very nice way. Okay, the other calixarins was not so effective, such as the acidic ones. The yield was almost the same that the reaction without calixarin. Of course, we need to, the fourth element, the reuse. It is possible to reuse the catalyst. It is, as I have shown you, you can reuse this calixarin in these reactions without compromise the efficacy. Here, there is a slight decrease of the efficacy when you use CX6, but it is okay. We have synthesized different kind of xanthanones, as I'm showing here. A very nice series of compounds. We have used different kind of phenolic compounds to obtain another series here. We got some X-ray diffraction for some of these compounds to prove to confirm the structure. And we have tested this compound in different kind of cell lines and also a non-cancer cell lines here. And we are looking here for some compound that has a nice selective index. It means they should be more toxic to cancer cells than the no cancer cells. And as you can see here, compound 6, and it has a very nice selective index when compared with doxorubicin, our positive control, another series of compounds that present a very nice, some example more than 1,000 the value. So it's a very, very selective compound with a low growth inhibitory efficacy. Look, the same of doxorubicin, but much, much more selective. And now this compound, we are testing this compound in animal models. So this is the sum up of the part of xanthanones. We have used a multi-component approach, a solvent-free, calixarin as a catalyst, and we have obtained a series of xanthanones that possess anti-proliferative activity, and this is very nice. From all I have told to you, we have used calixarin to access a different kind of heterocyte compounds in a nice and very good yields. For my surprise, I saw this article in this 10 days ago. You can ask Boom Boom about how fashion is the use of parasulfonic acid calixarin as a catalyst. I saw this very nice article. Congrats, Boom Boom. It's a very nice article and help me to direct my talk here, okay? Congrats to you.
Thank you so much, sir. Thank you so much.
Congrats to you, and I think your students. Congrats. And for the end, I want to bring here not how we can use calixarin as a catalyst, but calixarenes, because they are a multivalent molecule, they can be used as multivalent ligands to some process related with the recognition of a virus, bacteria, or some system for drug delivery, or to do a encapsulation of drugs, of DNA, to interfere in cell-cell communication. And this property is very useful when you think to use this kind of a microcycle as a bioactive molecule. We have prepared a calixarene that have shown to possess the ability to stimulate the immunological system to produce anti-cocaine antibodies. This is a very nice property because this antibody can bind to the cocaine and prevent it to go to the brain. So the amount of cocaine that reach the brain, it will be lower, and the effects too. This is the calixarene that we have prepared. We prepared 2 calixarene with 4 aromatic units and 8 aromatic units. And as you can see here, these compounds were able to produce antibodies against cocaine. And this vaccine, this immunogen here that I'm showing here, KLH-GNE, is the immunogen that was produced by the King Janda, the Professor King Janda group, and United States. Okay. We have access if these immunogens are able to decrease the amount of cocaine in the brain by using hydrodrug, trodate. These drugs is using to do some medical examinations. And as you can see here, this is the animal that didn't receive our compound. This spot here in white are the amount of this drug that reach the brain. Here is the vaccinated compound with V4N2, and this is the vaccinated animal with V8N2. As you can see, the amount of this drug that reach the brain is lower. And here the quantity amount of these drugs, as you can see here in the blood, in the no vaccinated animals, the amount is lower than in the brain, and in the vaccinated animals, this quantity invert. You have more of this drug in the blood than in the brain, proving that our calixarene derivative immunogen are able to reduce the amount of this drug that reach the brain. To finish, I want to present to you this Journal of Advanced Research. I am an associate editor of this journal. It's published by the Cairo University. And we receive it. It's a multidisciplinary journal. So you may be considered this journal to publish your future articles. And to finish my talk, I want to present this quote: don't give up on your dreams, or your dreams will give up on you. And when I'm talk about dreams, it is important to thank my students, because they believe in these dreams, they are part of this dream, and this dream couldn't be real, could be done or reach without them. They are a very important part of all that I have talked today here. Obviously, I want to thank the agencies that support our work. This is Belo Horizonte City, the capital of Minas Gerais state. I live here. Here is the campus of our university. This is the stadium, the Mineirão Stadium. This is the lake that are near to our university. This is our university, Federal University of Minas Gerais. All of you are welcome to visit. And this is all. Thank you for your attention.
Thank you so much, sir, for your very valuable and nice presentation. We learned many things like the calyxar in chemistry and the urea-based research. Thank you so much, sir. During the compilation of that review, I found number of references of your work. So thank you so much. I have already cited all those references. So thank you so much for your nice presentation. Hope our participants have learned many things from your lecture. So now this is the time. So dear participants, you can directly interact with the sir. So please unmute yourself if you want. Yeah, Professor Bimal Banik, sir. Yes, sir.
I like to give the chances to the student first, then after that I will ask.
Okay, okay, sir. Okay, okay. So any participants? Yes, Dr. Swati Meena. Dr. Swati Meena, please start your video as well. Dr. Swati Meena, please start your video as well. And
anyway, I wrote my email here in the chat, so you can send me an email.
okay, thank you so much. Yeah, Dr. Rakesh, can you can unmute yourself?
Yes, sir.
Yeah, please start your video. Yeah.
Sir, my question is related to the modification of drug. If sir can tell me about the modification of, because my work was on modification of drug, if sir can suggest any drug which
Sorry,
which
the modification. Sorry, the modification of.
Dr. Rakesh, can you please repeat your questions?
Yes.
Sir, actually, I want to know how can we modify any drug like anticoagulant or antihistaminic drug? Can we modify it in the laboratory for any synthesis method?
Okay, bem, well, I will talk about the way that we have done here, okay? To modify any kind of.
Dr. Rakesh, you want some library synthesis, means you can synthesize n number of derivatives. So by you making some derivatives, you want to change a drug's property.
Yeah, sir. Because I have modified an anticoagulant drug, that is coumarin. I already modified it. Just I want to know that any other medicines that can be modified in the laboratory, this kind of method, if sir have, if sir can tell me, so that I am asking.
Okay. First of all, you need to know, well, I will tell about how we do here, okay? How we do here. For example, in the case of urease, you need to know the biology of the disease that you want to modify, okay? And then you can try to do different kinds of substituent. For example, in that case, we have looked the urease inhibitors that have been published. We noticed the phenolic unity on them. And then we try to bring together the phenolic unit and the thiourea moiety. So you can have a hybrid that maybe possess a very nice biological profile, because without test, you never know. We have failed a lot. We have more failed than success, because failed is part of organic chemistry. We show only the good results, but for example, in the vaccine, we have tried different kind of molecules, and we got only two. So you need to know about the biology of the disease.
I got the answer, sir. I get it. I got the answer.
Thank you, Dr. Rakesh. Now, any other participants?
Only to finish, and if you want to share with me a more specific question, please email me, okay? Oh, I'm working with this. Do you have any suggestion? Will be my pleasure to contribute to it, okay?
Please share your email address, sir.
I just wrote it in the chat.
Okay, sir. Okay, sir. We'll find out. Sir. Thank you, sir.
You are welcome.
Okay. Bubun, if you do not have any other student, I like to ask the speaker.
Sir, I want to ask a question.
Okay, ma'am. Pooja, ma'am.
Yeah. Good evening, sir.
Good
sir,
evening.
I have got very trivial question that, sir, first of all, I would like to say that your lecture was actually very, very informative. Like, I am at my workplace right now, but I really enjoyed your lecture. My question is that if we are synthesizing some medicinal agent and the activity, for example, if I'm synthesizing some anti-inflammatory agent, and for anti-inflammatory agents, if it is non-selective COX inhibitor, then we have gastric problems also. But if I happen to synthesize a compound which is having lesser side effects, but at the same time the activity is comparatively lesser than the non-selective anti-inflammatory drug, so should we proceed for that particular moiety, or should we prefer the anti-inflammatory activity or the pharmacological activity itself? I mean, if we are weighing, should we go for the lesser toxicity or should we go for the better efficacy? It is my question, sir.
Okay, thank you for your question. Don't give up your dreams. because what you need to know is more information about it. For example, this compound is toxic, okay? And what is going on that this compound is toxic? Maybe it's a kind of a metabolization process, or you can do some modification to block the site. You can improve the stability. Since you know how to build the molecule, you know how to modify it, okay? You need to have more information about the molecule. Why this molecule is so toxic? Why this molecule is not so effective? For example, amphotericin is very toxic compound, but it is used. We don't have another. Sometimes you need to use it. And in some case, the toxic the toxicity is not a very important point. For example, in cancer is so bad, so destructing disease that you can allow some toxicity to kill the cancer cell. Do you know? When you are in a chemotherapy, you see the side effect, but cancer cell is so bad that, okay, you can lose the hair, but we need to kill this cell. So depend on what kind of disease you are studying, you intend to prepare some drugs, and you can modify your molecule. Since you know how to do it, don't give up your dreams, because with a small chemical modification, you can get a very nice improvement on your molecule, on your target molecule, lead compound. Okay?
Thank you so much, sir. Thank you. Thanks a lot.
Thank you so much. Now, Professor Tonik, you please ask your question.
All right. Professor Angelo.
Yes.
What are the mechanism of action of your xanthinone against cancer cell?
Okay. We are doing this now, but we have checked that these compounds are able to affect the tubulin formation, the cell division. But we need to get more information. We need to check another possible target of this compound. But right now, we are looking at the tubulin.
All right, only tubulin you are studying, not anything else.
No, now it is this. But if you have any question, please tell me.
Okay, my next question, very simple. Can you use calixarine, this kind of molecule, to create chiral molecule through asymmetric induction process?
Yes, you can use calixarine to do a stereoselective reaction. Yes, there are some.
Can you create asymmetric chiral molecule without using asymmetric influence, only using calixarine?
Yes, there are some calixarine that are chiral. If you use this kind of chiral calixarine, you can use them as a catalyst to do this kind of stereoselective process. There are some examples. I don't remember now one specific one, but it is possible.
Okay, I understand. Okay. And you a few minutes ago, you talked about toxicity of your molecule. Some molecules are toxic against cancer. You talked about it. Now, my question to you, when you have calixarine condensed drug, whether the toxicity can come from calixarine itself due to metabolic activation?
It is possible, but we have one example here from our group that we use calixarine together a toxic compound, and what we have observed is the decreasing of the toxicity. Okay, but in this case, the calixarine was not bounded to the drug. It's a kind of encapsulation process, and this process decreased the toxicity. But there are one patent from German, I believe, that where they describe a formulation for an antiviral drug, and they have used calixarine as one of the component of this formulation. I don't remember which one, but they are trying to use as they use cyclodextrin. You can find drugs, commercial drugs, where they use cyclodextrin, and now they are trying to use calixarin. Why? Because you can modify the calixarin. It's different from cyclodextrin, where you won't have hydroxyl, a primary and secondary hydroxyl on it. So it's a small type of reaction that you can use. But in calixarin, all aromatic reaction that you can use to modify it. So it's a very versatile compound.
Thank you so much for your nice answer. Thank you.
You are welcome.
Thank you, Professor Bunning. Now I'm requesting Professor Keglevich. Yeah, sir. You can ask your questions or you can interact with sir.
Okay, Professor Bubun, thanks. Good evening to everybody from Budapest, Hungary, where it is only afternoon. Professor Angelo Fatima, it was a very nice presentation. Congratulations. You are working on a very difficult field.
Yes.
I just have 3 comments, not questions, just comments. It was very interesting to see the use of calixarenes with chiral moiety in asymmetric synthesis. It was a fantastic and novel route. Also, it was spectacular when you showed the removal of ferromagnetic calixarene derivative by a magnet. And thanks for drawing our attention to the fact that urea produces carbon dioxide on the effect of ureasis, and this causes global warming. It's a terrible thing, and everybody should consider this. And finally, I hope you know 2 very famous calixarene chemists. One is from Hungary, Professor István Bitter, and the other one is he's my neighbor actually, and the other one is from Ukraine, Professor Kalchenko, Vitaly Kalchenko. Vitaly Kalchenko introduced organophosphorus functions into calixarenes. So again, congratulations. These were only kind remarks.
Okay, thank you. And tell him, please, that I'm very interested in this phosphorate derivative calixarene, because I believe that this compound should be a very nice anti-urease agent. If he wants to talk and do a collaboration, it will be my pleasure to test this kind of compound.
Okay, please. I promise to contact him because he's a very good friend of mine from Ukraine. Okay.
Thank you. Thank you.
Thank you so much, Professor Keglevich. Thank you so much, Angelo, sir. Now, is there any other participants who want to interact? Yeah, Anupriya, please unmute.
Good evening, sir. Good evening, one and all present here. First of all, I would like to thank you so much, sir. Thanks for giving us your valuable time.
Anupriya, can you please start your video as well?
Yes, sir. Your work, sir, which was extremely informative and helpful to us. Personally, I just want to share my views, interact with you. I don't have any question, but I just want to interact with you, sir. Thank you so much for giving us your valuable time. It was a great opportunity to have a talk with you, sir. And at last, I would like to thank Akal University. It was a very, very, very great opportunity for us, sir. Thank you so much.
Okay, yes. Thank you.
Thank you, Anupriya. Now I am requesting PK Chaturvedi, sir. You want to say something? Any other participants want to interact with sir? Because this is a nice opportunity for you all to that you can directly communicate with sir. And that is my aim or our university's aim, to provide you this kind of platform so that you can interact with such eminent persons. Yeah, PK Chadurpati.
Yes, sir. Lot of thanks, sir. Vanaji, sir. Lot of thanks lot of thanks to every speakers. Lot of thanks. There are no question, sir. No question. I am lot of thanks to you at our organization committee.
Thank you so much, sir. Any other participants? Dr. Vijaya, Dr. Jyoti Singh, Dr. N. Lata, Dr. Punita, Dr. Silpi Sinha. One participant raised. Yeah. Yes. Rabab Fatima, I think.
Yeah. Sir, good evening. Good evening, sir.
Yeah, good evening. Can you please
thank you,
start your video as well?
Sir, actually, I have a separate camera. It's not inside my laptop.
No problem.
I have to attach it.
Yeah, proceed.
Sir, Angela, sir, I just want to ask the use of calixarenes in transfection. In cellular transfection, you have mentioned in one of your slides.
Yes, there are some examples from the literature that they use this kind of calixarene, but one structural mandatory that I have noticed that you have to put some ammonium substitute in the aromatic ring, because without this, the efficacy of this transfection is not very efficient. But yes, you can use this to do some transfections, and there are some very nice articles, not from the chemistry of point of view, but the biology of point of view.
Okay, sir. You want to say you should add ammonium sulfate, right?
Yes, to improve this efficacy.
Efficacy of transfection.
I don't know. I don't have the answer why, but I believe this could be related with the interaction with some phosphate in the median. It's different from the reaction because now.
Right.
Yes.
Okay, sir. Thank you so much, sir.
Thank you. Now, any other participants? Anuradha Kumari. Yeah, Bikramjit Singh. Chandrakant.
Good day, sir.
Please start your video as well.
Good day, sir. Hello.
Yes, good day.
Sir, my question is, sir, my video is not starting. I think host has stopped it.
Okay.
Sir, my question is, whenever we do research or we are going to do some research, sir, from the previous literature reviews, so we design the molecule or then we synthesize it. But sometimes after that synthesizing the molecule, we came to know that from the in silico studies, we came to know that our molecules are going to be toxic. So, sir, these computational studies, are they absolute?
In my personal opinion, no.
Okay.
It is indeed a there is in my opinion, the best way to check the sound is not.
No.
Now it is okay, sir?
Can you hear me?
Yeah.
Okay. Let me tell you one case here from my lab. Okay. We work with forensic science too. We have developed some colorimetric method to detect illicit drugs. Okay. And we have some patents on that. And today, according to UNDC, 10 new psychoactive drugs are introduced in the world for week. This is a huge amount of new drugs, illicit drugs. And for most of them, we don't know the pharmacological effect. We don't have method to detect it. And we work, some of my students work with that in this area, okay? And we have prepared some compounds called NBOH that are illicit drugs. There are several cases of death in the world and some in Brazil, okay? When we perform the in vitro studies, we checked that these drugs are toxic to the neuron, and one of these compounds can decrease almost 50% of the neuron in hippocampus, part of your brain, okay? But all these studies were performed in an in vitro way. When we start the in vivo, what we disclosed, we noticed that these compounds are promising antidepressive agent. And this compound improved the learning process of the animals. I was shocked. My God, this is a toxic compound. This is a illicit drug. We perform the in silico studies, but in vivo, we disclose new potential for these drugs. So you need to do as more complete your data, more precise you are gonna be. Do you understand?
Yes.
Doing only the in silico studies, okay, it's okay, but the case is not closed, because you can get new information as you develop your research, okay? So do not close any case based only in one experiment, one approach, because you can lose good opportunity in your work.
Sir, then taking example of my research, sir, I have done work on the anti-inflammatory agents. So in that, sir, they have good innovation, about 72, I think 65%. Sir, but in silico, I have concluded that most of the compounds have been found to be toxic in silico, but otherwise they are good in terms of their efficacy and activity. So I should prefer the data of in silico, or I should go for alternative one?
I don't ever the answer, because you can go to the in silico, but you can say, okay, potentially these compounds are toxic, but you have to check in the in vivo, in vitro, and I don't know, you need to go further. You cannot say, okay, I will give up of this is toxic. This is my personal opinion, because you do your research in your own manner. Do you know what? Because, for example, amphotericin is a very toxic compound. Imagine a situation that we don't know amphotericin until now, and we discover this compound today, okay? And you do some toxicity experimental. Maybe amphotericin will never go into the drugstore, because the toxicity tell you it is very toxic. So my opinion is get the bigger view of your data in all aspects. And to do that, we will not do this alone. I do not do all experiments that I have shown here. I have several collaborators that believe in the project, that believe in this dream, and join me to go further. The vaccine substance, for example, I produce those compounds, but I need pharmaceuticals, I need doctors, I need immunologists, I need another several expertise to go further with the project, because without them, I will stop in the synthesis. Maybe I got primary results, and it is okay. But we have now the toxicity of those compounds in primate, the safety, cells, toxicity, pharmacokinetic. We are doing all of this, but not alone. I need help. And when we do this, we can have a big view of the project and the potential of it.
Okay, thank you, sir.
You are welcome.
Thank you so much, Vikram. Chitna, madam. Yes.
Hello, sir. Good evening. Am I audible to you?
Yes.
Yeah. Good evening, sir.
Yes,
My question. Yeah. My question to you is, we have something called as the heterocalixarenes. Could you please put some light on it regarding the application into the green chemistry?
Okay. Can you repeat the question, please? I don't know if I understood it correctly.
We have something called the heterocalixarenes, something like the calixfurans or the calixpyridines. Another macrocyclic polymer as such.
Derivative.
Yeah. Can you please put some light on it, on its applications on the green chemistry that we can utilize into the drug industry?
I have no example about this until now, okay?
Okay.
We have working only with the classic calixarenes. Those derivatives, I never tried to synthesize them, and because my career start with calixarene, but now I am decrease this research and start to work on vaccines and forensic science.
Okay.
So I don't have the answer and an example of the use of. I saw some articles, but it's still there are a lot of work to do in this area.
Right.
Maybe you can do this to feel this part of the use of this calixarene. But I have no clue even how to synthesize them, because it's a kind of different chemistry from the original one. Sorry about that, but I don't have the answer.
No problem, sir. Thank you so much.
Okay?
Yeah, thank you so much. It was indeed nice talking to you.
It was my pleasure. Thank you.
Thank you, sir. Thank you so much.
Yes, Dr. N. Lata, you please.
Sir, good evening.
Yes.
Good evening, sir. In this PPT, all slides are very informative and very useful for us. I am working in Semiconductors College, assistant professor in Department of Chemistry. can you suggest any simple work regarding this for our PG students? We are done in a very... Hello, sir.
What I have done is simple.
Simple work.
Yes, it's simple. As a research in Brazil, and even nowadays, we don't have a lot of money to do research. It's not like in other countries. And when you are beginning, you need to start with simple things. But to be simple, it's not mean is not important. And as you can see, and if you compare with the previous speaker, I was fascinated with the chemistry that they have shown. And what I have done is simple, but usually what I do is connect with chemistry with the biological activity, chemistry with the technology application. I start with the application, do a kind of inverse engineering, and go to the synthesis. I don't start with the synthesis. My primary attention is given to the need. We need urease inhibitors. We need a colorimetric method for detect illicit drugs. We need anti-cocaine vaccine. Okay, now I know the need. So I think how as a chemistry I can contribute with that. So my primary vision is to the need. What is the need? And you can do simple things to answer, to feel that need. And this is the manner that we do here, because we don't have a huge grants for research, but we have dreams, and we fight for them as a research to contribute with our country, to form good persons, good researchers. And this is what I think that the youngest need to keep in mind. Don't give up your dreams. Because it's hard, it's hard. Who told it could be not hard? It's hard. It's hard to live. But when you will decide to live, when the life is not hard anymore, maybe it's late for you. You need to live now. You need to think, to fight for dreams now. My dreams in my academic career is this project. And I'm so happy that I found some youngest that are so embracing with these dreams. And dreams come to the truth, come to the life.
Okay. Thank you.
Thank you, Dr. Lata. So is there any still, because we are almost harassing Professor Fatima, it is around 1 hour 30 minutes. So
it's
still,
okay.
Still, it is a good opportunity. That's why I'm still continuing because any other participants? So if not, then thank you so much, Professor Fatima. Thank you so much for your valuable time, and thank you so much for your nice explanation. And definitely, thank you so much to Professor Bimal Bani, Professor Keklevich, and Professor Ansu Dandia, Madam. Thank you so much. Thank you so much for all other participants. So, dear participants, today's conference is, I think we should stop now. We'll meet again tomorrow at 9, start at 8:45. So next, yes, Ansu. Yes, Ansu madam, please. Dania madam, please, you can share your views, or if you have any questions, ma'am, please. Madam, please unmute yourself.
Yeah.
Yes,
Actually,
ma'am.
I would like to share my experiences because I am listening all the lectures since morning, and I would like to congratulate you for you have collected the galaxy of great scientists, not only from India, but abroad also. And recently the talk of Dr. Angela was also very nice, and all the talks were very informative and motivating for our students and our younger fellow colleagues. So I hope they will follow. And I would like to really congratulate you from my heart that you have done such an excellent work to collect.
Thank you. Thank you so much, ma'am, for your always inspired. You are always inspired me, and thank you so much. If students and participants learn something, then my hard work will get successful. Otherwise, it will be totally meaningless.
You are working very hard since long time, and all these your speakers, they are really very eminent, and means very high quality research work they have done. So that will motivate our students and fellow colleagues.
Thank you,
sir.
Thank you so much, ma'am.
Thank you.
So thank you once again, Professor Angela. Thank you so much for your valuable time. Thank you so much. So dear participants, we should stop here now. We'll meet again in the day 2 sharp at 8:50 a.m. Thank you so much. Thank you.
Thanks a lot.